Hi there! On the bench today, we have an Echophone EC-1 shortwave radio or communications receiver from about the mid-1940s era. So this is a unique little receiver in the fact that it really is just an All-American 5 or AA5 radio with one additional tube used as a BFO or beat frequency oscillator so that you can listen to CW or Morse code. This little receiver goes from the bottom end of the broadcast band, which is 550 kilohertz, all the way up to 30 megahertz, so it can be classified as a general coverage receiver. Now, this has got quite the story behind these little Echophone EC-1s. They were known as a morale receiver for the soldiers during World War II, and a fellow by the name of John has done a really nice write-up on his website. He's dedicated an entire page of his website to the restoration of one of these. And he has a lot of the original advertising literature there, and he also redrew the schematic and did a really nice job on that. So I think you'll enjoy his little write-up. So what I'll do is I'll put a link to his website just below this video. If you're new to YouTube, if you look just below this video, you'll see a little Show More tab. If you click on that, the link to his website will be under that. So hats off to you, John. You did a really nice job on the write-up on this little receiver. So my story on this receiver is I was visiting another fellow radio collector enthusiast, a friend of mine. His name is Larry Fennell. He's a really nice fella. And I go over to his house every now and then and we chat. And I was telling him about the idea for my next video, which is basically, restoring a simple receiver and then explaining the way a superheterodyne radio works. And I glanced over at this little Echophone here and I took a look at it and I said, I think this would be a really good idea. This receiver would work very well for the explanation of this video. And he says, well, just take it. So I said, wow, thanks, Larry. So I brought this home and here we are now. So just like in all my other videos, sit back, relax, enjoy, and follow along with me as I go through and completely restore this receiver. And we'll talk about, the dangers of All-American 5 radios and transformer and transformerless radios. And then in the end, I'll explain how a superheterodyne receiver works, and we'll use a scope, and I'll make it as simple as I can, and you'll see really just how easy a superheterodyne receiver is. So let's get into this and start restoring it. Before we get into the restoration procedure for this Echophone EC-1, we should examine its construction. I'll also explain the function of the knobs and the switches on the face of this receiver. Now you'll notice on the top here we have 4 small retaining screws and a grill. Just below this is an internal speaker that's facing up and it's mounted to this lid. Now when I put my hand on the lid of the receiver, it'll kind of give you an idea of the size of how small this really is. I'll grab my industrial-sized coffee cup here and we'll compare it to it. You can see really how small this receiver is. You can pretty much block the dial with a coffee cup. Now the paint on this receiver is in relatively good condition and I want to keep it that way. So you'll notice that I have a soft medium underneath the receiver itself. Now my desk surface is a polyurethane surface and it's really hard. Now when you're working on a receiver like this, you're turning it upside down and it's on its face and all sorts of different things. And when you're clipping capacitors out and changing things, you're getting solder on your bench surface and little tailings from trimming capacitors and resistors and stuff like that. If this is directly on that urethane surface and you move the receiver like that, you're going to have a big scratch in it. So it's always nice to have a soft surface underneath so that when you're turning it around, you just don't risk damaging this, and you really don't want to damage the face of the dial here. Which brings me to another story. Before I started doing this video, I had to polish this corner because it was completely diffused. You couldn't even see the dial. And what had happened is it looks to me like somebody had scraped a sticker off with a knife and scratched the plastic up. It looked like it was completely ruined at that point. There were really deep scratches. My fingernail could catch in the scratches. So I thought, at this point, what have I got to lose? So I got some 1000 grit wet sandpaper and some plastic polish and worked away at every one of the scratches, and it did a pretty good job. I'm not really done yet, but it's enough so that we can see through the plastic. You couldn't even see through this area before. It also looks like there was some form of an impact here. It looks like there's a little bit of a, almost like a stress mark in the plastic. So something may have hit but it's really not all that noticeable. I don't want to change this because it has a really nice amber glow. It's kind of gained over the years of being exposed to light. And these pieces of plastic are riveted to the face of the receiver, so I'd have to take all these little rivets out. So I kind of want to keep this original. I can imagine when we get this going here and look at the dial light on the inside glowing, it'll probably look really nice with this amber colored plastic. It'll have a really nice warm glow. If I replaced this, it would have a, it would just be a clear piece of plastic. It wouldn't have this kind of a feel to it. So it's kind of nice. I like that. So if we look at the face of the radio here, we can see a bunch of dials. Now, the main tuning and band spread, volume control, and band switch, these are all really common to all communications receivers of this era. So the main tuning dial just really is a coarse tuning for this needle here. And then we have a band spread here, which is really a fine tuning. So how the band spread works on most communications receiver is they have little parts of the dial that are designated where you sit the needle on, and then this acts as kind of a fine tuning for that portion of the band. It takes that piece of the band and spreads it out, hence band spread. So this really is just a fine tuning dial. We have the phones and speaker switch here. I would really not suggest that you ever use the phones position in a receiver like this because one side of the chassis is connected directly to the AC line. I'll get into talking about the safety considerations about this receiver here in just a little bit. We're going to make this receiver a lot more safe than it was when it came from the factory. So I'm just going to leave mine in the speaker position. This is an on and off switch and a volume control. This is a beat frequency oscillator here, which is basically just an internal oscillator that allows you to listen to Morse code or CW. And if you're really lucky, you might even be able to listen to a single sideband transmission. This is the band switch. We have 3 separate bands in here, and the bands are little half moons. So in the position number 1, we're on the broadcast band here. I don't know if you can see that without the glare. This is really hard to keep the glare off this because this is kind of a dome. So you can see position number 1 here, that's the broadcast band. That's 0.55 megahertz or 550 kilohertz all the way up to 2 megahertz. And that's in position number 1. So that's a broadcast band plus the 160 meter amateur band and a little bit more. When we go to position number 2, that's the second half moon. That's just under 2.2 megahertz all the way to just above 8. And when we go to position number 3, it's 8 megahertz all the way up to 30 or just a little bit over 30. Here we have a standby switch. It says off and on. So the standby switch is used for amateur radio operators, or if you're going to use this in some form of communication service where there's going to be a transmitter off to the side. When you transmit with the transmitter, you have to turn the receiver off. Basically, the receiver's internals stay on, but what this does is this just opens the cathodes to a couple of tubes to basically mute this receiver so that it doesn't squeal. Because what happens is the microphone that you're talking into will hear the speaker, and you get that feedback, kind of a squeal that you would get with a public address system. So by turning this into the off position stops that from happening. So this is really only for amateur radio or for a transmitter of some sort if you have that off to the side and you want to talk on a transmitter and use this as a receiver. So that really is the external of the receiver here. So next we'll take a look what's inside this receiver and see how the years have been treating this little Echophone EC-1. Let's take a look at the bottom side of the chassis, or the circuit side, of this Echophone EC-1. Now, when I received this receiver, it didn't have a bottom cover, but the person that owned this some time back was nice enough to put the feet back on. Why no bottom cover? I have no idea. So when Larry received this, it basically just sat at his house for a few days, and I went over to visit him, and he just handed this off to me for the video. So he knows about as much about this receiver as I do. And I talked to him about the bottom. He said, I might have a piece of aluminum out in the garage. Let's see if we can find a nice little aluminum panel. And he did. So we cut this aluminum panel to fit. Now, when I say I cut this to fit, this panel does not come right to the edge of the radio. It's recessed in from the edge just a little bit. And the reason I've done that is when the radio's sitting upright, you don't want to see a shiny edge on the front of the radio while you're looking at the radio. You want this to kind of be disguised, so it is recessed in just a little bit. I haven't drilled any of the holes yet, but I did round off the corners so that it matches the contour of the radio. So I'll have this all on the bottom of the radio when this is all finished. You should never run a radio like this without the bottom on, ever, just because of the risk of electric shock. And of course you have components in here that if something happens to them and they want to, say, explode, like capacitors, they have vents on them. You can see on the top of this cap here, that little punch mark. That punch mark is a vent. So if this builds pressure inside, that vent will open and it will spray electrolytic paste and do all sorts of bad things. So you want that shielded inside of a metal case. So you always want a bottom on a radio like this, or any time that there's exposed circuitry, and especially in this, there's some high voltage in this all over the place actually, so you got to be very careful. So for those of you that aren't familiar with point-to-point wiring, this is what point-to-point wiring is. Really, it's just capacitors suspended in midair, and resistors also, and tied off by their leads to tube sockets and terminal tie strips. So the terminal tie strip can be used as a tie point to run a resistor and a capacitor off of in a wire, and then usually the capacitor will go to a tube socket, or something like that. And that's what point-to-point wiring really is. Now this particular wiring scheme was used for a very long time before they started the development of circuit boards, and circuit boards started taking over full force. Now, of course, circuit boards are way more cost effective because a person has to physically wire and put all the pieces in and solder these all in, whereas of course you can populate a circuit board by a machine and have a machine solder the entire circuit board for you. So this is much more labor intensive. But it did work for the time, and there's a lot of very neat radios out there that are point-to-point wired, and amplifiers also. So each of them have their perks a little bit. Of course, I won't get into the perks of point-to-point and circuit board wiring. I'll save that for another video. So now this particular radio here is in a pretty bad state of disrepair. Many people have had their hands in this over time, and I can tell that it looks like it's gone through a series of partial rebuilds and it's been left alone. So I think what's happened is somebody has probably messed this up so badly inside that other people haven't been able to bring this back. Now, we have parts like this that are just floating in here. You can see these capacitors. I don't know what you want to call this, a capacitor octopus. It's just, look at this, just floating in here. So this has all got to come out. It's tied to the chassis here. And if somebody was going to start to rebuild this and use this old Elna capacitor, this is just junk. You shouldn't be using this kind of stuff. These are, this is well past its due date, this capacitor here. Not so sure about these ones, but this one for definite sure. So this has all got to come out. We can see that they've replaced a tube socket down here. This is an octal tube socket, and it's now mounted in with 2 screws and 2 nuts. So this isn't an original tube socket, because we can see the originals are riveted to the chassis where this is mounted by that screw and that nut, and the socket design's a little different. So I think what's happened throughout time is somebody had put different tube sockets in 2 spots of this radio, and then just before I got it, or some point in its life before I got it, somebody put this tube socket back in and started to try to rewire this radio back to its factory self. And why I say that is this tube socket over here is a Loctal tube socket, and all the rest are octals. This whole radio is an octal style radio. Now, a Loctal tube is much like an octal, but it has a lock on it, and they were used in Philco radios and a lot of automobile radios. I'll just zoom in on that socket there. You can see at the bottom here they've got this little clip, and when you put the tube in, there's a little dimple in the bottom of the indexing pin, and it locks into that piece. So they're really good for automotive applications because they won't vibrate out of their tube socket or anything like that. So why they've put a Loctal tube socket in here, I really have no idea. A lot of receiver modifications way back when, they were trying to get rid of mixer noise, and they would replace the mixer noise. They're trying to deal with things called partition noise, and they want to get rid of ENR, equivalent noise resistance. So people were really experimenting in the day heavily with different kinds of mixer tubes. And some, of course, mixer tubes operate quite a bit nicer at the higher frequencies, so they might have been trying to make this a little bit more of a performer on the upper bands. I really don't know the story behind it, but those are some common themes of why people tried to do this back in the day. So this is a really old mod because if you look at the solder here, the solder really looks original. It's done very well. I'll zoom back into that for a second. You can see the solder, you know, it looks well. The wires are cloth and they've got dirt, kind of a hair-like dirt on them. And the original wax caps are soldered to this socket, which tells me that this was done a very, very long time ago. So there's various states of rebuilding inside this receiver. Now we can see here that somebody has done a real nasty thing here. They've taken a piece of this trimmer cap right off. So there's a spring-loaded piece on this trimmer cap, and it really is a compression style trimmer. And this is a little mica tab here, and then there's a screw in the center just like here, and then of course when you open that screw, this little part opens up and changes the capacitance, and then when you tighten the screw down, it tightens closer to this other metal surface, and of course changes the capacitance again. Now somebody's broke this right off. We take a look here. You can see where they've broke or cut or ripped the tabs right off. You see it's kind of supposed to have this bow here and run onto this tab. They've ripped it right off, so I don't know what the deal is with that, so I'm going to have to go in there and replace this. The mica still looks like it's in good shape, and I can still see the threads in the hole, so the little screw isn't stripped. So I'll try and resurrect this piece here. Now, of course, in all old radios, you have to completely remove all of these waxy capacitors because they leak. Now, they don't leak physically, they leak electrically. Now, capacitors are only supposed to pass alternating current, not direct current. And when these capacitors start to leak inside, basically these are a paper and foil capacitor. So the paper has gone acidic in there, and what's happening is it's actually starting to leak. It's becoming more of a resistor. So instead of just passing AC, it's now starting to pass direct current. And when a capacitor starts to pass direct current, this really is turning into some form of a resistor. Now, when they pass direct current through them, it biases up the following stage, and when it biases it up, it causes the tube of the following stage to draw heavy current, and it causes failures all over the place. It'll open IF transformers or oscillator coils, or just even burn the tube out itself, open plate and cathode resistors. So these capacitors always have to go. Anytime you see a wax capacitor, you don't even question it. You don't even check them. You take them out, you turf them. They all have got to be replaced with a modern polypropylene cap or something equivalent to that. Now, it looks like somebody's been in here and they've already started the capping process here. We can see that they've added some newer style caps here. I believe these are poly caps. Now, I don't think that they've actually done any research to find out which end is the band end or which side would be the outside foil or the outside metallized polypropylene layer. So I'm going to end up having to do that. I'll probably just remove these. I'm not sure if I'm going to save them, or I may just replace these completely with just some different capacitors that I have. So these will all have to go out. Now, if you want to see how you locate the band end of a metallized polypropylene cap or any kind of capacitor that is deemed nonpolar, my Hammerland HQ120 video, I use a small oscilloscope and I show you how to actually locate the band end. Every one of these capacitors does have a band end, it's just that they don't mark them for some odd reason now. So that's at that point. What else can I tell you? When we look at the chassis here, this is a series set radio. So what that means is all the filaments of the tubes are hooked in series, and then of course when you plug it in the wall, it adds up to around 120 volts or 110 volts, whatever they've worked it out to be. And the tubes all light up, and they're kind of like a series Christmas light string. When one tube goes out, all of them go dark, and you have to test all the tubes to find out which one has the open filament. So when they do that, they don't need a transformer, and that cuts the cost of this receiver quite dramatically because you don't need that big block of iron hanging out inside the receiver. Now, in this receiver, we can see that we have rubber grommets attaching the chassis to the actual case of the radio. You see that there? Now, one side of the chassis on these series set radios is connected to the line cord directly. Now, back in the day, they didn't have polarized outlets, and that made this radio kind of dangerous because at any point you have a 50-50 chance of making the chassis of this radio live, whether you plug the plug in the wall like this or turn it around like this. They weren't polarized back in the day, and there was no larger a spade on the plug and then a smaller one, right? So the larger one on the normal wall plugs nowadays is the neutral, and the smaller tab or spade on the wall plug is the hotline. So in order to make this receiver a lot less dangerous and kind of bring it a little bit more into modern times, we're going to put a modern polarized line plug on this, and we're going to also change around some of the wiring to the switch. The hotline that comes in from the AC outlet will go directly to a fuse first. And then from the fuse, it'll run up to the switch, and then from the switch into the circuitry. So there's always a fuse, the very first thing in line with the line cord. And since the line cord is polarized, if your house is wired correctly and to code, it keeps the chassis of the radio neutral. And on top of that, we do have a little bit more protection that this chassis is completely isolated from the case by these rubber washers. So we're going to have to replace all these. You can see these are all decaying and they're all finished. I'll zoom into that washer a little bit there. You can see how bad this is. So this all has to be replaced. So we're going to have to remove this chassis completely from the case of the radio. And if you look at the ones that are holding the main tuning condenser here, they are also bad. So we're going to have to remove the main tuning condenser and replace all these rubber grommets under the tuning cap. Now they suspend the main tuning condenser for a bunch of reasons. One is for vibration, and another is to isolate the RF ground because they only have one lead coming off for RF ground. The thing isn't strapped directly to the chassis. So I'll get into explaining that a little bit later. So these rubber grommets definitely need to go. They're all crusty and they are all finished. So aside from that, in order to remove this from the case, this Echophone EC-1, they really didn't think that this was going to, I guess, come to this point. So they've riveted the switches to the face of the radio. So we're going to need to desolder all the wires from the switches and mark them. From this switch, and this switch. These ones we can undo the nuts on the front of the radio that hold this potentiometer and this selection switch here. We can undo the nuts and then they'll come back. So we're pretty good that way. So it's just these wires that we have to desolder. There's another two on the other side of this switch here. And then this chassis should basically come out. Now the reason I have to remove this entire chassis obviously is to replace these rubber grommets here and this one here. And of course, if I want to get to the inside of this plastic dial face here, I have to take this entire chassis out to clean the inside of the plastic, so it all has to come apart. On top of that, we're going to need to remove the top of the radio. So the top of the radio is held on by these 3 screws on this side, and there's 3 on the other side. And when we look in the back side of the radio here, it really is in pretty good condition. So inside the radio here, in order to tune these IF transformers, we need to come down from the top. So this top is going to have to come off and go missing for a little while. So we'll put that off to the side. And we have, these are the factory tubes in here, it looks to be. The Lochtel tube is missing down in there. And we can see that one empty tube socket back in there. This one here is the replacement tube socket. The rubber grommet here is looking like it's in pretty good condition. It looks like they recently replaced that. It's a little bit loose, so I'll do something about that. The dial strings don't look too bad. If they're in any rough condition, of course they're going to get replaced while I'm inside this. So that's pretty much a rundown of the chassis. This little transformer that you see back here is the audio transformer. So that's basically converting the impedance, the high impedance of the plate in this vacuum tube to the low impedance of this speaker. That's what the little transformer is in there for. And I think that's about all I need to cover at this particular point. So when I come back, we'll start disassembling this entire radio, and I'll show you how to take notes and what to do in order to make sure that after you've disassembled your radio, you know how to put it back together and you don't have wires hanging all over the place like this. And I think many people in the past have just gotten lost in this thing, and it's just been left in so many, it looks like there's so many stages of people working on this and then just leaving it. It really is kind of bizarre. So let's get into the next portion. Before we remove the chassis from the case of the radio here, or remove the top of the radio with the speaker, we want to desolder the wires off these switches, because these switches are riveted to the face of the radio and they won't come out. Now you'll notice that this switch here is 2 black wires and 1 white wire, and it does matter which way these black wires go, and you don't want to put them on the wrong way. So what you want to do is mark one of these wires with a piece of tape or just something, and then take a picture with your camera phone or just a digital camera, or you can draw it out too. It doesn't really matter, whatever works for you. And that way in the end, when it comes to reassembly time, you don't have to figure out and use the schematic to find out which wire goes where. That really is wasting time, and it is kind of a pain if you do that, so it's better to do this all right now. So you want to mark these ones here. There's another switch here which has 2 completely independent switches on it. There's one switch on the top and there's one kind of tucked down in here, and it's right against the face of the radio here. So I'm going to need to remove the chassis back to get at those, to desolder those. But these here are just 2 single pole, single throw switches, so the wires really don't matter. You can put them on this way here or on this way here. It doesn't really matter. So you don't need to get too incredibly picky about these. And of course it's the same for the other half of the switch. Now don't get them mixed up or anything. As long as they're like this, you can do this down here with these 2 contacts or this up here with these 2, but don't mix them up whatsoever. As I say, these are just 2 independent, separate switches. They're basically just 2 on-off switches. And it's the same with this one here. This is an on-off switch. So what you can do is you can mark them if you really want to get the wires right back on the right post. And then of course, as I say, take a picture with your camera phone or the digital camera, or as I say, draw it out again. That's absolutely fine. So that's what we're going to do now. Is I'm going to remove these wires, mark everything off, and then we'll come back and we'll take a look at the actual disassembly here. You don't need to disassemble or desolder any of the wires on this potentiometer here or on this wafer switch. All we're going to actually do is remove the nut on the face of the radio, and then of course this will just come back. So this would be a lot of work to desolder all these wires and to mark them, and it's absolutely unneeded. So just leave these ones here alone. I'm now ready to desolder the wires from this switch here, and you can see I've marked the center wire with some whiteout, and I put a little dot on the face. The nice thing about whiteout is it just scrapes right off and you'd never even know it was there. This little white dot here on the wire might remain there. I can scratch it off. I'm pretty sure I can get it off, so I'm not really too worried about it. If you're worried about this in the end, you can always just get a little black marker and just mark over top of it, and you would never even know that that little white dot existed if it really bothers you that much. Now you don't want to just cut these wires off and then worry about it later. Reason being is you're still going to need to clean these off to put the wires back in again, and you'll need to restrip them, so you're kind of creating a lot of work for yourself. So what you want to do is just desolder the wires from the switch itself. So what I do is I get in here, heat the area up, and then just desolder it like so. Move it around a little bit like that. And then of course, you don't want to be too rough with this, because if you are a little bit too rough, then you might break the actual wire or the contact off the switch. So you don't want to do that. And then of course the wire is still here on the end, and it still is nice and strong. When you're moving this wire around, you're not moving it to actually break the wire off. You're just moving the wire around so that when the little bit of solder that is left here, because this is hot, you don't want it to get hard again and then hold this steady. So if you keep moving it, the solder won't actually bond to this and it ends up free, and then you can just move it off like that. If you find that you've weakened the wire at all in here, you're going to want to cut it, restrip it, and then put it back in here again. But you can see that's a nice clean terminal right there, and we're ready for reassembly again. So what I'm going to do now is do that to the rest of all of these contacts here and get these all loose, and I'll be back. Alright, I've now got the wires desoldered from those switches here. I'll remove this lens again. I'll zoom on into the switch. So you can see I've removed the wires, and I just kind of moved them off to the side here. And then of course these ones here, same thing for this switch contact. And then over here, same thing again, and I've twisted them together. So these are desoldered. I still have to get at the bottom side of these ones here. So now that I've done that, I want to loosen these two switches off here, this wafer switch and this switch slash potentiometer, the on-off volume switch here. So what I'm going to do is turn this around like so. And in order to do that, we need to remove these knobs. And in order to remove these knobs, we need to take these little set screws out here. So I will open my toolkit here and grab one of my screwdrivers. And all you do is you just pop this in here like so. And this one here, and this here, like so. That's pretty much how easy it is just to get down to this level here. So in order to remove this potentiometer and this switch, we're going to need to undo these two nuts here. And they look like they're around a 1/2 inch. This one looks like it's, yeah, they look like they're about 1/2 inch. So I'll grab 1/2 inch here. And we'll put this on here. And we'll just loosen these off like that. And of course I'm going to put these somewhere so that I don't lose them. There we go. And the nice thing about these is they've got a little washer behind them too, so it really does kind of reduce the scratching of the paint here. So usually when I get a radio like this that doesn't have washers, I will put a washer behind it. Looks like the threads on this one are a little bit rough. So very tight. So as I say, yeah, it's kind of nice that they do that. So it really does save the paint. So now these are loose, this is loose, and this is loose, and this will pretty much just slide back. So next what I'm going to do is remove these screws on the side here. You can see that. I'll remove this screw here, and this screw here, and same on this other side here. And when I come back, I'll slide this back, and we'll take a look at that. This is coming apart rather easy, I guess because this has been apart so many times. You can see the nuts are kind of stuck in these cups over here. So these just, they're, you know, very, very easy to get at. You just stick a screwdriver in and it seems like you don't even have to hold the nut on the other side. That little cup is holding it. So I imagine it, in the end, I'm going to probably have to free all this up because I'm going to have to replace these grommets. But now this is free. So now what I can do is just kind of move this back. We're not going to jam up on anything here. I guess the rubber is a little bit stuck, and there are some indents I see here. So there's a little bit of an indent here on the case. So I've got this about far enough back now that I can get down at those two wires down there with my desoldering tool, and I'm going to end up desoldering these. So now there's two wires on this one terminal here, and there's only one wire on the other one. So now what I'm going to have to do is I'll probably twist these two together, and then that way I'll know that those two go to one, and then I'll have the other one off to the side. And I may even mark it also so that I just don't forget. Okay, I've got all the wires desoldered off this switch now. And what I did is I put just a little solder ball on these two, kind of a browny yellow kind of wire here, and they're joined together so I know that these two just remain connected. And this one, this black wire that's off this side of the switch here, this one side right here, just goes right to the chassis. So that makes life quite a bit easier. So these are just have a solder ball and they're put together. Now if you're going to do a little solder ball down in here like I did, make sure that you don't drip and hit the window, because that would completely destroy the window. So you got to be very, very careful about that. And I was extremely careful that that I didn't do that. So now that we're this far, what I'm going to do is flip this over here, and I'm going to undo the screws on the top, which are these screws here, and there's 3 on the other side as well, and I'll remove the top of the radio, and that should allow us to completely disassemble this whole thing. Okay, we just about have the top completely disassembled. I'll just undo this one screw. Now I've also disconnected the speaker wire inside. It's just a plug. So you just pull vertically on the plug and the plug comes out, and I'll show you that in just a moment. So here's the top, and it just basically comes out like that. And this is the plug. Just pull that vertically right out of this little socket right here. And this kind of clips into the front to hold the front tight to the radio, so it kind of shims into this area here. And we're pretty much ready to take this right apart. It's now a lot looser because this was kind of pinching the case together and holding it tight on the chassis. So of course, before we put all the rest of the radio back together, and before we put this one piece on, we'll have all the rubber grommets in and everything, and this will allow me a lot more room to work on this. And of course, we need this top off in order to adjust the IF transformers. So this is going to need to remain off. And of course, if we have to do any dial alignment or anything like that, or fool with anything on the top here, we're going to need this open anyway. So the speaker will be the very last thing to go back on this radio. Now that we've removed the speaker off the top of the radio here, the sides have kind of popped out a little bit and it's loosened everything up. So in order to get this chassis out, it should come out relatively easy because everything is just disconnected. And there it is, just comes out like that. You can see parts and pieces falling off, and you can see the case here. So what I'll do is I'll move the chassis out of the way here, and we'll take a look at the case. I'll just put this over here. So you can kind of see, I don't know if you can see that in there, a little bit of an impact in here, what we were talking about earlier. So I'm going to get in here and clean this all up. And these switches here, of course, have got really dirty contacts in them from sitting for years. So when the contacts get dirty, they develop a thing called contact resistance just through tarnish or whatever is, in this switch, dirt and all that kind of stuff, just accumulation from over the years. So I've got my Nixie tube counter over here, and what I'm going to do is I'm going to set this up and I'll show you what I mean by contact resistance in these older switches. Now that I've got the chassis out, we can see the switches clearly. And we can tell that that chassis hasn't been out of this radio for a very long time, or the case of this radio, if at all ever. So you can see here, the amount of dirt that's just laying in here is incredible, and that's just all piled right on top of this switch. There's a good chance that that's inside that switch too. If we look at the adjacent switch, we can see the adjacent switch has got a hole in the top here, and if, of course, there's any crud going to sit on here, it's just going to go right into the switch. So we want to clean these switches really thoroughly. Of course, there's another switch right over here, and you can see that the top on that one is completely open also. So all that crud's going to lay in that switch. So what I'm going to do is go into the garage and, of course, blow these out with my compressed air. Now, I have an air compressor, and that makes life a little bit easier, especially when you're dealing with this amount of dirt here. But if you have, a can of air for cleaning keyboards or anything like that, you should be okay. You can use that to dedust this. Just blow all that stuff out. Just don't inhale this stuff. It's really not too good for you. And once you get the switches all kind of, the dirt out this way, then of course you want to put some contact cleaner in them. Now I've got my Nixie tube meter here set up on the side, and I'm just going to get things positioned here, and I'll show you what I mean by contact resistance in these switches and how that dirt really affects the contacts. Let's take a look at the contact resistance of this standby switch here. So I'm using my recently restored Dana digital Nixie tube multimeter here. It's on the 200 ohm scale, so it's 199.9. When these leads are shorted out, they've been zeroed out, so it reads 0 ohms. So what I'll do is I'll turn the switch on and we'll see what we get. So we get 0.1 of an ohm. Now, when I move this switch around, you'll see something happen here. And I'm just touching that black part of the switch. Do you see that, how that jumps? That's dirt in the contacts inside this switch, and there's corrosion. It's creating contact resistance, and that's really what creates a staticky switch. So what needs to be done is all these switches need to be blown out with compressed air, and then a liberal amount of contact cleaner sprayed inside the switch, moved around, dried out, and then sprayed again, and then dried out. And then we should get some pretty good readings on the meter. So this is a really, really touchy switch here, and I can just touch it and it goes all over the place. You can see here, it's just by me putting a little bit of force on this black plastic here. Now, one warning about contact cleaners, you got to be very careful with contact cleaners. A lot of contact cleaners will attack paint So you got to be very careful when you spray it on the back side of the switch. If you don't know that your contact cleaner is going to harm paint, what you want to do is use it on an inconspicuous area of the paint in the cabinet somewhere and move it around a little bit and just see if it removes the paint. If it doesn't remove the paint, you're usually good to go. If it does remove the paint, you do not want to use that contact cleaner, because if you spray it in the backside of these switches, it's going to leach through the switch and will probably get under this, and it would completely destroy your radio. And you definitely don't want to get it on any plastics. That stuff really attacks plastics. So be very careful with your contact cleaner and try it before you go just hosing things down, or you might cause a lot of damage to your radio that you're going to restore. So next, what we're going to do is check out the chassis and see what we've got ahead of us with that. Here's the chassis out of the Echophone EC-1. You can see it's in relatively good condition. It's a little bit dirty here. I'm pretty sure I can clean this up. You got to be very careful on the face. You don't want to use any kind of heavy cleaners or anything like that. You got to be very gentle, and you kind of experiment as you go. So I'll end up cleaning this up. The dial is in very good condition and everything there. On the top, we can see here this tube socket that they've added. You can see how they've kind of drilled off that hole a little bit to put this Lochtel tube socket in here. So we'll get rid of that and put the original tube back in there. You see the tube lineup is all pretty good. The chassis just got dirt on it. It's in really good condition. Missing a tube over here. The dial strings look very good. A little bit dirty. Let's grommet on the light here that's kind of floating around. It's supposed to be down here in this hole. So other than that, the top side's looking good. Got to replace these grommets. The grommets are bad. As said again, we got to go and replace these grommets on the side of the chassis. You can kind of see I've taken one out. They just look like a standard grommet, and they're really, really crusty. Look at that. So that's all got to come out. And the underside we've already been over. So this is what it looks like when it's out of the actual radio. Gives quite a bit more room to work on things, and a little bit easier to move around and stuff like that. So I do have a little bit of work ahead of me here. I have to figure out what they've done everywhere. It almost looks like a complete rewire job. These dog bone style resistors look in very, very good condition, so I'll measure them and see how far out of tolerance they are, and the ones that are way out I'll replace. This one here almost looks brand spanking new. So that's where I am at this point. So what I'm going to do is I'm going to start recapping this and changing grommets and doing everything I need to do in order to make this happen. And when I've got some more to tell you, I'll be back. What I'm focusing on first on the bottom side of this chassis is replacing these rubber grommets on the main tuning capacitor or condenser, whatever you want to call it. So I have to remove these coils to get access to it. Now this one of course isn't so important, but I have to remove this anyways to replace this Lochtel socket that somebody put in. So I've got them both loose. But in order to remove this oscillator coil and capacitor assembly here, all you have to do is remove two screws, one from this side and one from this side, and they thread right into the chassis. And of course this wire here attaches to this side of the tuning capacitor, and this wire here attaches to this side of the tuning capacitor. You also want to desolder the wires from these two terminals on the bottom side. Now yours is going to look completely different than this on the bottom, and especially in this area, because as I say, somebody's put a different tube socket in here and this is wired altogether different. This Lochtel tube doesn't have a grid cap on the top, so he tied into the bottom here instead of using that terminal on the top. The terminal on the bottom and the terminal on the top just are connected to each other, and it's the same for this side. So there's two separate capacitor assemblies in here, and you can either use this one or the top side. Now of course this Lochtel tube may have been a better performer than the 12K8. I'm not really quite sure. I know for sure that there's shorter leads between the socket and the tube, and this is shielded under the chassis, so somebody may have tried to improve this, and it doesn't look like they actually got it to work. But the whole idea here is to put this thing back to stock and try it out, and then of course after we know what the thing performs like when it's stock, well, maybe then we can do some modifications and improve this just a little bit. Of course not going too incredibly far from its originality. So that's where I am now. It looks like a real big mess under here and kind of scary with all these wires all over the place, and this whole area is going to be basically stripped out. So this is just the beginning. So now what I'm going to do, I've got all these desoldered. I'm going to undo these nuts on the main tuning condenser or capacitor assembly here, and I'm also going to put some tape on the pulley where the dial string is attached to, so when I drop this forward that the dial strings don't come straight off of the pulley, so that way when I put it together I don't have to fool around with that for too long. So I'll put this thing back in with the new rubber grommets, and that'll get this out of the way, and then I can remount this. And then what I'm going to do is I'm going to resolder all the wires that I've detached that I'm not going to really fool with. I'm not going to leave things unhooked for long periods of time, and that's just good practice so that you don't lose where you were. So when I put this back down here again, I'll resolder this wire into here, and I'll resolder this wire into here, and of course once I get this side back together with the socket, I'll put this antenna coil down and I'll resolder this wire that's from the antenna jack here. It goes right to the antenna jack here, and then of course solders onto this little tab here. I'll put it all back together so that way I don't have to think about that in the end. And of course I'll resolder this to here. This I'll probably leave open just for the reason being that I think this whole area is just going to end up coming straight out of here. But I'll see how that goes and how things feel at that particular point in time. I've also measured some of these dog bone style resistors, and I'm not really too happy with the ratings. So I'll probably just go in here and pretty much mass out all of this stuff. I haven't tested these capacitors. I don't know if they're paper or mica at this point, but I'll test them for leakage and everything. And if I'm leery about these whatsoever, they're out of there too. So the whole idea, of course, is to make this thing dependable and work like it did when it came out of the factory. And that's what we're going after here. So this is where I am at this point. In order to ease the removal of this capacitor here, the main tuning capacitor from the chassis, I'm going to remove this face here, the dial. So what I'm going to do is remove the light. The light just kind of unclips like that. And you'll notice that there's a little needle on the bottom here. You don't really have to worry about that needle too much because when you remove this, it's just going to kind of spring up just a little bit. So I'll just remove this. And it also allows me to clean this with ease. So hold on to this. And remove this side here. And I'll just lift it up like so. And there. So now I'm pretty much right at the tuning capacitor here. And when I was telling you that I was going to put some tape on here so that the dial string doesn't come off, what I do is I usually put just a little bit of tape on this and maybe a little bit of tape on the bottom half. If there's a lot of dust on here, you'll have to wipe that off or the tape won't stick. But, you know, that's how I'm going to do this for now, so that way this doesn't kind of go sproing and the spring lets off and everything. Of course, it's going to get loose when I lift this off. And then, of course, we have this side here, which will probably also do the same thing. So I'll put some tape on here because there's two separate capacitor assemblies on this one. So this one here is for the band spread, and it moves two plates in and out for fine tuning. And then, of course, this is the main tuning assembly here. And this is what I was telling you about where the grid cap went over to the 6K8 tube. This terminal here attaches directly to that bottom one that I was telling you about. And this is one capacitor assembly here, and then this is another capacitor assembly here. So that's what I'm going to do now. I'll just get the tape and undo those screws and move this off to the side and replace those rubber grommets. I'll just give you a quick look at the tape. So what I've done is I've put the tape over the pulley like this, and I've taped it together to the pulley like this. And you can see I've used the hole in this pulley here. You can see this is just loose, but what I've done is I've used the hole in the pulley here, and I've kind of put the tape together. You know, when tape sticks to itself, it bonds quite a bit tighter. So I put it here because these two kind of join like this. One of the dial strings comes in and goes like this, and the other dial string comes in and goes like this. So there's one piece of tape holding this, and then on this one there's two. There's one on the bottom and one on the top. And when I move this over now, these dial strings, they're going to get loose, but it's going to not derail from the actual pulley. And I don't want to have to go through and redo all of that at this point. Here's a shot of the capacitor and its little legs poking through the chassis, and you can see the nuts on the bottom here. So what I'm going to do is undo these nuts and then remove these grommets, and you can see how the grommet is on this side of the chassis also, but you can also see how these threaded shafts are mounted right to the main tuning capacitor there. So when you have this up, if you have a little bit of extra time, you might also want to clean under there while you're at that, because it's very hard to get under this main tuning capacitor when it's bolted down to the chassis here through these grommets. So that's what it looks like under here, and then of course we have the one right at the back here that we're going to have to do also. Alright, I've got the new rubber grommets installed here, and they just kind of pop in the holes, and then of course these little shafts are going to go back through these rubber grommets when I put this back down, and you can see how the dial strings are still kind of holding on and the tape is holding them, so that way when I put this back in I don't have to go about redoing all of the dial strings right away. So that's where I'm at now. So now I'm just going to put this straight back down and in through the holes of these rubber grommets. You can see these little legs here will go through the holes, and I will tighten that back down and on to the next step. The new rubber grommets are installed. You can see here and here, and then of course on the back side there's one installed also. And one nice little bonus about replacing these rubber grommets is it kind of lifts this back up again. Now, if I take the face, I haven't cleaned it yet and I haven't remounted it, but if I take this face and I put the face on and I center these holes right about there and there, centered, you can see in the face that shaft in the center that's coming out, it's almost perfectly centered to the face now. Before, it was almost rubbing the bottom half here. In fact, it may have been. I can see some wear marks here and here. So that's a really nice bonus of replacing those little grommets, is it lifts this main tuning capacitor or main tuning condenser back up again, and everything is all aligned. So this is all back in. You can see the dial strings are still on nice and tight. I did remove this little band spread pointer just for ease of moving back and forth, and I didn't want to hurt the little needle. So in the end, when I go to realign everything, I'll just place it back on the string there. At this point here, I've got all the wires desoldered from this Lochtel tube socket here, and I've removed all the parts and pieces, and they're kind of just off to the side. So now I'm going to undo these two retaining screws and nuts on each side and remove this tube socket and fit this again with an octal socket instead of having this Lochtel socket in here. I've now put in a factory style tube socket here again, so I've removed that Lochtel and I've put an octal socket back in. Now it's the same style as the factory, with the exception that of course this is screwed in because the person before me had drilled out the rivets, and you can see they've actually off-drilled a hole here. So this is mounted in with screws and nuts, whereas the factory is of course riveted in. And of course the factory tube sockets have a number stamped in them, whereas this one doesn't. Now on this corner, they've also replaced this tube socket down here for some odd reason, and it's a different style of tube socket than this. So I have another tube socket just like the other ones. In fact, this is pretty close to the exact same tube socket, with the exception that there's no tube numbers stamped into it. So I may as well replace this one here too, since there's no wiring on it yet or anything, and that way we'll have a complete matched set of tube sockets on the chassis. I've now changed out the capacitors and the resistors in the bottom side of this Echophone EC-1 chassis, with the exception of these three silver micas and this one dog bone style resistor on the headphone jack. This resistor tests absolutely fine, and I never plan on using headphones anyways. And these three silver micas test fine as well, and they rarely ever fail, so why change them out? I've also populated the two tube sockets that I replaced here. There's also a lot of wiring errors on top of that, and that's all been gone through, so this is getting really close to actually being able to test it out. I've also made some important safety improvements, and if you own a receiver that's an All-American 5 transformerless series set, you may want to consider this as well. On a lot of All-American 5 receivers, the one side of the line cord is soldered directly to the chassis, which of course makes the chassis a little bit of a shock hazard, especially when you have external antenna connections and stuff like that on the rear of the radio. So by putting in a polarized line cord like this greatly reduces that chance of shock. Now when I say greatly reduces, that depends on your house, if your house is wired correctly, and of course if you wire your cord correctly. Now the wide blade on the new cord, this is a brand new cord here, the wide blade is the neutral side and the skinny blade on the plug is the hot side. Now the neutral side goes directly, of course both these wires go directly through this shielded pipe here. This is a high heat shielded pipe. It runs through here, and the neutral side gets soldered directly to the chassis of the receiver. So the wire itself is soldered to this lug here, and then the lug is soldered through an external wire to the chassis, making that even more safe just in case the screw was to ever come loose. The hot side runs directly into this fuse down here, and this fuse then runs off to the switch and then through the switch back to the tube, and there's also a safety capacitor that's running from one side of the line to the other here. Now these safety capacitors are another thing that you should install. and they're XY rated capacitors, and you might want to check that out online. If you're going to ever tie any capacitors from the chassis to the line or just across the line, you need to use the appropriate capacitors. You need to be very safe about that. Regular capacitors have the ability to short and of course make the chassis hot, or some of them will explode and cause fire. You want to make sure that you have the right capacitors installed. So they're called safety capacitors, and you may want to look up XY rated safety capacitors, and you should come across a lot of information on these capacitors. Now you're probably thinking, why put a fuse in here when of course this is running through the switch and directly into a 35 volt filament in a vacuum tube? Well, technically that filament could act as a fuse, but there's a lot of things before this tube that could fail. If one of the pieces in this switch happened to break off and fall against the chassis here, of course that's going to make one of these, the chassis of the switch live, and if that happened, this fuse would just annihilate instantly. So this is an absolute value fuse that I've put in here. It's rated at 1 amp, and of course this radio is going to draw somewhere in the hundreds of milliamps somewhere, but this is an absolute value just in case something was to happen like that. In any other case, of course, probably the filament would end up opening. Keep in mind that these receivers never had any fuses in them. If you wanted to get more accurate with the value of the fuse, you could measure it. First turn the receiver on and of course measure the surge current, and then see where it settles off to, and then of course make the appropriate decision for the fuse at that point. I just opted to go with a 1 amp fuse because I feel for my own purposes that that will be absolutely safe. Again, if you're working on any of these receivers or you're going to work on your own receiver, you're doing so at your own risk. These receivers do, obviously have high voltage in the bottom of them, and of course if you're not careful you can get shocked, so you need to be very, very careful. You're doing this at your own risk. So there's a whole bunch of safety improvements that you can make to this particular receiver alone, and I'll start explaining with the actual line cord, and something that Echophone really didn't think about in the day. In order to do that, I'll just focus in here. Just take the wide-angle lens off. So if you look down at the chassis here, you'll see the line cord runs in through this rubber grommet here, and then of course it goes in through this heat shielded pipe, which is just really a high heat coating on the pipe. And there's a little plastic retainer clip here that holds the cord tight to the chassis. Now originally when these receivers were built, they just tied a knot right here so that would act as a strain relief. So if you pulled on the cord, you wouldn't pull the cord out and of course, cause it to separate from its solder joints. Now there's a problem with that. Just any normal line cord with a knot in it has very close clearance to the tube socket pins here that you solder to. So the solder lugs on this tube socket are very sharp on the edges, and if you rotate that line cord, that knot will rotate and you get a chance of cutting into the wire, which of course creates a hazard. So by having this wire come in and go on a sharp angle here, and then of course through this plastic retainer clip, and then of course through this shielded pipe and down along the bottom side of the chassis, makes this a lot safer. And of course these pins get very warm because there's a power tube on the top of this. It's the audio output tube, and they get pretty toasty. And of course these pins get hot, and of course they can melt through the plastic of your line cord. So there's a whole bunch of reasons to actually do this. And of course having this line cord tight against the chassis reduces hum. These two resistors here do get a little bit warm, but this is quite far away from that line cord. I can slip this directly right underneath here, no problem. It's about 1 centimeter above that. So, and of course it has this pipe along it to keep it shielded and protected as long as it runs across the chassis, and as it of course runs into the fuse, and as the neutral side is connected to the chassis and of course soldered at this point. So those are a few safety things that you probably see a piece of fuzz floating around here, as some safety things that you're going to want to do if you're going to run a radio like this. Now I notice a lot of All-American 5 receivers do have a tube socket really close to where the line cord comes in. If you find that it has that and you're replacing the line cord in your receiver, you want to make sure that there is no chance of that knot in the line cord touching any of the pins of the tube sockets, because they will slice through, and I've seen it on quite a number of receivers. So this little plastic clip has just got a screw through it, and there's a one small screw right above where the line cord grommet is, and that holds that in. So this is, tight. You could never pull that out. It acts as a strain relief, and of course makes things quite a bit safer. So that's pretty much it for the safety improvements here. As you can see, it has Nishikon brand new caps. When you're putting in the new electrolytic capacitors, you want to make sure that you use a really good brand. These are all 105 degree C rated capacitors, and they're a really good brand. So you want to make sure you use a Nishikon or a Panasonic or a Rubicon or United Chemicon or something like that that has a really good, has a good name, because you don't want to put cheap caps in. The values of these caps are a little bit higher than what was in here. They are both 47 microfarad, which is absolutely fine. Nothing will happen to the rectifier. And of course, these are 450 volt rated caps, so they're well beyond what they need to be. I have a number of these capacitors, and I just like to replace them all the time. So, I really don't want to have to come back into the bottom side of this radio again. So by going a little bit overkill allows you to not have to do that ever again. These two resistors here are supposed to be a 7.5K resistor. These are two 5 watt 15K resistors in parallel, so that makes around 7.5K. And they do get pretty warm. Not warm enough that you can't put your finger on them, but they do get pretty warm, so I'm glad that I went with these two 5 watt resistors, so that'll keep things quite a bit cooler. And, just basically I've been through this whole receiver and just replaced everything that kind of needs to get replaced, put the appropriate capacitor values where they're supposed to be, and made some slight performance improvements. Some of the resistors that you see that are supposed to be, say, 400 ohms, if you use a 390 ohm, you're going to be just absolutely fine. Don't get too incredibly picky with these values, as long as they're, pretty close. Like this is supposed to be a 2 meg resistor. This is a 1.8 meg. Absolutely fine. This is in the AVC line. And if you see a 50K resistor in a receiver like this, if you put a 47K resistor, you're going to be absolutely fine. This thing isn't, a very high precision device, and these resistance values really don't mean all that much as long as you don't drift far from their value. Of course, understanding how a receiver works and what the circuit is will, help you choose whether to go higher with the resistance or a little bit lower with the resistance. But in most cases, as I said again, these receivers really aren't all that incredibly picky as long as you stay around the value. 50K resistors aren't all that common nowadays, so a 47K is the next closest value. And as I said, don't get too crazy about the filter capacitors in a radio like this. Yeah, you probably don't want to use like a 400 microfarad capacitor at 450 volts because you risk blowing the cathode strip off in the rectifier tube if you have a power surge or you unplug your radio or turn it on and off again. So you don't want to drift too far from the actual values. A 47 microfarad capacitor on each side of the resistor in the schematic is absolutely fine, and you will have no problems with that. In fact, I find 47, I buy my capacitors in bulk, and I find that 47 is kind of a nice fit for all, most of these old receivers like that. So you can go with a 33 if you'd like to, which would be absolutely fine. 2 33s would be okay. Again, don't get too incredibly picky. The reason that they went with lower value capacitors back in the day is not just because of the vacuum tube, it's because they were cutting costs, and it also has to do with the size of the capacitor and what they could fit in. Remember, this radio is from the 40s, and everything was pretty big back in those days. So what I may do is try to power this receiver up, and before I put it in the case, and I guess I could probably try right now. So what I'll do is I'll get an external speaker ready, and I'll get this hooked up to my Variac isolation transformer here, and we'll just turn it on and see if the thing powers up. So it was pretty miswired. I'm hoping that all the IF transformers are still okay. I didn't bother ohming out the IF transformers. They're pretty self-explanatory. If you turn the thing on and you're pretty sure that it's wired correctly, if it's dead silent, you know that something's probably pretty bad. But that takes, you know, a relatively short amount of time to do with an oscilloscope to check those IF transformers and to even check the oscillator. And I'll go through all that in the end, and I'll use this radio to really briefly explain how a super heterodyne receiver works. And if you're unfamiliar with this, you'll really see how incredibly simple these receivers really are. The moment of truth has arrived for this little Echophone EC-1. Let's give it some power and see if we can make it make some noise of some sort anyways. So I've got the alligator clips all hooked up here, and it's just temporarily hooked up. I would like to do the rest of the tuning and working on it when it's in its case, just for the reasons being that this thing, when it's laying on the bench, is kind of, it lays on its tuning capacitor, and of course the tubes are, you know, touching the this little towel I've got under here and everything, and it's kind of tipsy and wobbly. So for the testing, we'll you know, first just preliminarily test it like this. Of course, it makes it quite a bit easier to work on because all the switches will be hooked up and everything on the face, and we can't really align it or do anything with the dial missing on the front. So everything is kind of just binding right now, but this is good just to try it out and for the first time see if we can make this radio make any kind of noise. So all these alligator clips are just tied in all over the place, as I say, just to, you know, roughly test this out. So these two little alligator clips here run over to the test speaker that I've just put on the bench here, sitting right here right now. You can see here I've got this alligator clip here and this alligator clip here run over to the voltmeter over here that I've got, and this voltmeter is just monitoring the line voltage that's going to come out of my AC supply over here. So this is a variac, this is an isolation transformer, and this is a dim bulb tester on the top. So these just act as a current limiter. So when I turn this radio on and slowly turn this up, when I get the radio right up to about 115, 120 volts, these two little light bulbs should glow somewhat dimly. If they glow bright, then I know I've got a problem. So I'm expecting a dull orange glow. Now how these are going to look in the camera, it might look a little bit brighter in the camera than it does to me, but I'll mention that at the time. But they should glow a very dim orange, or just above that. About the color of a hot kitchen element is about the color that this should glow if this radio is going to be working correctly. So let's see, what else can I tell you? I didn't mention these three little blue capacitors that I've added to the antenna jack. Now this is a good idea to add to any of these old radios that have an antenna coil in the front end that isn't isolated from the actual antenna jack itself. These three blue capacitors are just three more safety capacitors, and what they do is they block any DC from getting onto this coil, and they will also limit the current just in case that there's a line isolation fault or anything like that, so that you don't burn out the coils. These coils on here have some really fine windings on them, and if any current whatsoever is applied to them, it'll open up the antenna coils. And this unit is an extremely hard unit to fix because they've kind of put all the coils on in layers, or they've wound them on here in certain areas, and they're measured and everything like that. So if this coil goes open, it's a very, very hard thing to fix. You're probably going to end up looking for another one, and it goes for most of all these old receivers. And some of them, they've got some pretty interesting winds on them. So by adding the capacitors back here, you're just giving yourself a little bit of extra insurance that you're never going to hurt this. These capacitors back here don't affect the performance of the radio in any way. All they're doing is they're just protecting this. So you can pretty much be assured that if you do put these in, you will never have any problems with this antenna coil. So that's what these are for. They just basically isolate this coil. So it blocks DC completely, and of course if there's AC applied to this jack by accident, it will limit the current that will get into this coil here. So that's what that's for. I've got this hooked up to an external antenna outside. It's just tied up to a piece of coax here. Is a long wire antenna outside, and we'll use that to see if we can receive anything off of this. I just installed two knobs on these dials here. I don't know where anything is. I don't know what band this is on or anything, but we'll just turn it on and see if we can get any life out of it. So what I'm going to do now is I will turn on my variac supply, and I'll bring the voltage up to about 60 volts while watching the dim bulbs, and at that point, hopefully we don't have any bright bulbs happening. So here we go. Okay, I'm up to about 60 volts right now. I'll turn off the light. You can kind of see the dim glow of the little dial lamp down here. It's starting to glow. And the dim bulb tester isn't showing any light. Now don't pay attention to that one. That's just the on lamp. These are the two up here that we're going to be concerned with. So all is looking good. I'll bring it up to about 100 volts. I'm up to about 100 volts, and I can just see a very, very faint glow in the bulbs, which is good. And the dial light down here is still looking good. I do hear just a little bit of hum out of the speaker. So this is a good sign. It's coming to life. Alright. And I'll bring this up to about 115 volts. And there we go. And that is glowing about the brightness, maybe just a little bit brighter than a kitchen element to my eyes. So if it looks bright in the camera, that's just because of the camera. It's the same with this little light bulb down here. In the camera that looks blazing bright, but to me it's about the brightness of a night light. I can see the filament structure and everything in the bulb, so it's just the camera being kind of sensitive. And we're at about 117 volts now. And as I say, I do hear humming in the speaker. I don't think you can hear that. I don't see any deflection on the meter on my camera here. So I'll give it a little bit of volume. And I already hear music, so this is a good sign.
Variety. You know, it's important to have a variety because, you know, some things on nutrition, some things on news.
Oh, it's working pretty well so far.
John, can you hear me? Excuse me, trunk in the left lane. And look at LQ.com. La Quinta takes care. The corner.
That's really quite surprising. It's basically just coming to life like that. Okay, let's try another band. That sounded like the broadcast band. So this should be a shortwave band of some sort. Now the fact that we're hearing static, is telling us that the oscillator and the IF chain is working here. If either one wasn't working, the radio would be silent. Not sure how active the shortwave bands are right now, or even where this is. There is some action here. The station there.
It's up to the province. They could say is that there's
Station there. That's pretty much the end of the dial. There's some sideband. So it is receiving. It's not bad. So I'm not sure which way I turned this. Try and move that this way. I think that's the end of the band. It sounds like we've gone back to the broadcast, so I need to go to this end. So the shortwave bands are quite active. So that's a really good start. So that's very impressive. That's a really good start for this right now. I'm really quite surprised that it's come to life this well with this capacitor missing here and everything. So this looks like it's for the broadcast band because it goes to the largest coil here. So I'll have to experiment with this and see why they've done that. Maybe for some reason it just sat wide open and they removed it. I don't know, but I'm going to check this out here, and when we go through the alignment, we'll check all of that out and see how this all works. So right now, this is a really good sign. It's working, and I'm very surprised myself. I figured, you know, this thing was so malaligned and so miswired when I had this that, you know, it would be just in outer space for alignment, and we would be lucky to get any sound if a squeal. So it's come to life. So maybe that's a little bit of a testament to how robust these little Echophone EC-1s really are. So on to the next step. Before I go putting the radio back in the case, I want to give this plastic a bit of a polish on the outside here and of course on the inside. And I've got this really nice plastic polish. It's a Meguiar's plastic polish and works very well. So what you do is you just put a little bit of it with your finger on the face like so, and then you get a nice soft rag, and then what you do is you just work it in like this, and you can kind of hear it has a very slight abrasive in it. And as long as you just keep polishing it and working away at it, you'll eventually get rid of all of the little scratches and all that kind of stuff that's on the face here. Now there's a couple of them that are kind of deep, and I'm going to work away at this a little bit to try and polish this plastic up just about as much as I can. And of course I haven't even touched the inside yet, and this is really, you know, just a labor of love. You're going to take a while if your face has got some scratches on it. You really have to work away at it. So that's what I'm doing right now. And I've also taken the dial face here, and I've cleaned up the dial face. So I've used a very, very mild detergent on it, and of course you want to be very cautious as you use your detergent, because depending on what condition the face of your radio is, the dial face, if you use a strong detergent, it might remove the actual lettering and the numbering on this. So you want to be very, very careful. So I basically took some mild detergent and slowly worked away at it, and this is about the best that I'm going to do. You can see that some of the numbers have faded just a little bit. Now that's not from me doing the polishing or the cleaning, they were just kind of faded, but I was very, very careful because I do not want to degrade the face of this receiver at all. And that's about the best that I'm going to get out of it, and it's not too bad. It's a little bit darker around the edges here, but that's kind of outside the viewing window, as of course this is gonna, you know, sit in there like that. So the next step is I'm gonna put this back on the receiver and put the dial, put the actual needle back on, and then put the band spread on, and then after I've polished this up, I'll put it back in its case. When you're polishing this, you want to be very careful that you do not put this on its face like this, because this is a bubbled window, and if you push on this too hard, you're going to cause issues. You might even crack it, so you really don't want to do that. So when you're working on this radio, it always, you know, is going to be, you know, like this or on its side, but it will never be on the face, or you will damage this window. Maybe the previous owner did that, and that's how they put that little indent up here. I'm really not too sure. Before we put this chassis back into the case of the radio, what we want to do is we want to align the main pointer needle and the band spread scale needle to the capacitor's end stops. And how we do that is we rotate the capacitor in the back. So this is the main tuning capacitor is now meshing. So now it's fully meshed. And when I mean fully meshed, that means that all the plates that are on the capacitor are inside each other. So, and that'll be at the bottom end of the dial here. So when they're like that, what you can do is put some tension on this and slide the needle until it lines with the line. Now if you find that this is too tight, you can reach behind and just hold the capacitor closed with your fingers and rotate this until this needle is even with this line that runs across here. And then when you've done that, rotate this to the other side and just make sure that it's even on the other side. And then this needle is aligned so that you can do the RF alignment on the bottom. And now when I say RF alignment, I mean that we're going to be adjusting the oscillator to make this track properly on the top here. And the same goes for the band spread scale. What you want to do is rotate this right to the end, and on the back side of this little needle here, there's three little fingers that look like this, and then the string goes through the fingers like this. So what you have to do is pull the string out of those fingers, and then this will just float free, because there's glue on it. And then after it's actually free, put the string back in like this, and hold this tight and align this to the 0 mark. And then once it's aligned, rotate this up to the top and check that it's even at 100. If it's even at 100 and it's even at 0, leave the string where it is in those little fingers and put a little dot of super glue on it, and that will hold the string tight in this needle, and you've aligned the band spread scale. And both of these have to be aligned properly in order to do the oscillator alignment on the underside so that this will track properly, and of course the main needle will track properly also. Before you put this back in its case, you may also want to add a little bit of oil to some specific points on the main tuning capacitor. This is the band spread capacitor here, and you can put just a little bit of oil in here, right there. And right at the front of the capacitor right here, you can also add just a little bit of oil. And then the same goes for right in the ends of the main tuning capacitor here. You can put a little bit of oil in there, and you can also put a little bit of oil in the front here. So basically we're lubricating this little bearing down in here, and then the one on the rear, this one, and this one. And now you can do the same with these. These are the shafts that tune the dial string here. Now you'll notice that this dial string is right at the front. You may not want to put any oil on the front here, because if it gets under this dial string you might get slipping. So you want to put just a little bit on the rear here, and then on the rear. And there's also a few pulleys here that you can put some oil on the shaft of the pulley. Don't put oil in the pulley where the string rides, but put the oil right on the actual shaft. This little rivet that sticks out here is what you would want to get that on. And then that of course will smooth things up quite a bit. Just a word of caution when you're lubricating up your radio and all the shafts and such. I notice a lot of people like to put oil on the bottom of the band spread scale here so that the needle moves a little bit smoother along here. Well, that's really not too advisable, because what happens is the oil leaches underneath the paint and eventually it causes blisters, and then the paint starts to peel off. So the best thing to do is just leave the needle alone and let it travel along the paint's surface. That way you don't risk ruining your band spread scale. One thing that really contributes to this is the radio gets really hot because it has vacuum tubes in it, and everything gets soft, all the paints get soft, and then they absorb the oil, and then of course you get that blistering effect. So best just to leave this little area here dry. Keep all oils and everything completely off the face of the dial here. The Echophone EC-1 chassis is now back inside the case. When you put this Echophone chassis back inside the case, you need to have one more safety capacitor. And that safety capacitor connects right here on the actual case to the chassis. Now, if you don't have this capacitor installed, you're going to get quite loud pronounced hum in the speaker, because this entire case is now connected to this volume control and it's isolated from everything. So this capacitor is really quite important for a few reasons. So you can see it went back together pretty easily. It's all back together and ready for us to do an IF alignment. Now that's the first thing we need to do. We can't do any RF alignment or anything like that until the IF is aligned. And I'll show you two different ways to do this IF alignment. So the first thing to do if you're going to do an IF alignment on this Echophone EC-1 is you need a signal generator that will put out 455 kilohertz, and there is no tone on that, so there's no modulation. And your signal generator should be capable of putting out at least 100 millivolts worth of signal. And this is already set up, so we're at 455 kilohertz here and at 100 millivolts output, and we're ready to put that into the receiver. The second thing you want to do is get your oscilloscope set up, or your vacuum tube voltmeter. I prefer to use the oscilloscope for the alignment, but a vacuum tube voltmeter will work fine as long as you know that the signal coming out of your signal generator is exactly at 455 kilohertz. In order to get this Echophone EC-1 ready for an IF alignment, there's a few things you've got to do. First of all, disconnect this from your isolation transformer. And the isolation transformer, of course, is connected to the line. You can't do any alignments on a receiver like this unless you have an isolation transformer. That's the only safe way to go. So disconnect this from your isolation transformer. Then what you want to do is go to the band switch on the front and make sure that this is in the broadcast band position, and it's at the lowest end of the band. So this capacitor here is fully meshed, so that should be down around the 550 kilohertz mark, right at that end of the dial. Right to the stop is absolutely fine. Once you've done that, you're going to take the lead that comes from your signal generator, the signal generator that's at 455 kilohertz, and this is the shielded lead. You're going to take the shielded lead and clip that shielded lead to the case of the tuning capacitor. Now I'm talking to the case. The case is what's connected to the chassis. Don't connect it to the plates or anything, and make sure that this isn't going to touch the plates. Now what you're going to do is you're going to get a alligator clip and put a 0.02 or a 0.01 microfarad capacitor in an alligator clip, and this is really handy to have when you're doing an IF alignment on a receiver like this. If you don't have an alligator clip, what you can do is you can solder this capacitor right to this point here on the main tuning capacitor, and that's fine, but I find this much easier. So what you're going to do is you're going to take this and you're just going to clip it right onto the grid cap of the 12K8 tube. So this is just sticking up like this. And now you take the center conductor of your lead and just clip it on here like that. And that completes just the first part of getting this ready for an IF alignment. The next step is to attach an oscilloscope to this Echophone EC-1 to do the IF alignment. We'll also use a vacuum tube voltmeter here in just a little bit to do it, but I'll show you how to do it with the oscilloscope first. So what we're going to do is take our oscilloscope probe leads. We're going to take the negative or common lead of our oscilloscope and we're going to clip it to the chassis, and we'll take the actual probe itself and we're going to clip it to the insulation on the last IF transformer's output wire to the diode plates of the 12SQ7. Now the reason that we're doing that is because we don't want to load the circuit. If we tie that oscilloscope probe directly to the pins on the 12SQ7, what's going to happen is when we tune this last IF transformer here, we're going to also tune the oscilloscope probe, and we don't want to do that. So the scope probe is just lightly coupled to the insulation at the last IF transformer, and what that's doing is, again, lightly coupling it, so we probably only have a picofarad or a couple of picofarad of capacitance between the two, and it's enough just to sniff the signal here. This is the cap on the 12K8 where we're feeding the signal in. So it's running in here, going through this IF transformer that we're going to tune, getting amplified by this 12SK7, running into this IF transformer, and then coming out to the diode detector plates. And these diodes are also forming an AVC rectifier, which is creating negative voltage here to turn these two tubes on or off depending on the signal strength. And I'll get into explaining that here when I actually explain how this whole circuit really works. So we're tying the scope here to pin 4 and pin 5 to the insulation on the lead, which is right here. You can see this kind of a greenish looking wire here. That's where it's getting tied to, right here. And then on the top, of course, where I showed you where we put that alligator clip is where we're tying the signal generator in. We're now going to use an oscilloscope to do the alignment of this Echophone EC-1. So you want to set your vertical sensitivity, or your volts per division, to 100 millivolts per division, and you also want to set your time base to 1 microsecond per division. Alright, now we're going to apply power to this Echophone EC-1 through an isolation transformer. Remember that you can't really perform any of these alignment steps unless you have an isolation transformer, and of course you need to know what you're doing, so if you're following along, again, you're doing so at your own risk, so be careful. So I'll now turn on my isolation transformer here. We'll see the dial light get bright for a second. And now the receiver is warming up. So as the receiver is warming up, these are the 4 capacitors that we're going to adjust. We'll call this one number 1. This one here we're going to call number 2. This one we're going to call number 3. And this one we're going to call number 4. So when I focus into the oscilloscope screen a little bit later, you might want to remember that this one here is 1, this one is 2, this one is 3, and this one here is 4. So this is the first IF transformer, and this is the second IF transformer right here. So you can see we already see a signal on the screen of our oscilloscope, and all we're going to do right now is look for maximum amplitude in order to tune this. So we'll start with this one here. You need an insulated screwdriver to do this. So we'll pop it inside of this capacitor here. I can get it in there. There we go. And now we'll watch the screen, and I'm going to tune this for maximum amplitude. So if you pass it, you just back the screwdriver up and tune it for maximum right there. So now that we have that one at maximum, we're going to come into this other one here. This is number 2 now. And we'll tune this one. If you pass it, again, you just back up and peak it again. So that's the maximum there. Now we'll go into capacitor number 3 here. And now we'll go into capacitor number 4. And now we've peaked it. So now what we can do is we'll just double check to make sure that we're good. We'll go into number 2 here. And into number 3. And to number 4. Remember, if you pass it, just go back. And that's the peak. And that's how you align the IF of a small receiver with an oscilloscope and a signal generator. So next I'll show you how to do this with a vacuum tube voltmeter. We're now going to align the 455 kilohertz IF with a vacuum tube voltmeter. So where we're going to tie in is right here on the AVC line. We're not going to tie in before this 2 meg resistor. We're going to tie in after. So this side here has a filter on it. There's a filter capacitor, and that cap is right up in here. So we don't want to tie on this side of the resistor, but we want to tie in on this side of the resistor. So this is a 1.8 meg resistor like I pointed out before, but that's absolutely fine. So I've replaced that 2 meg with a 1.8. And this is the point where we're going to tie the positive probe of our vacuum tube voltmeter. Now you want your vacuum tube voltmeter set on negative DC volts, and of course what we're going to do here is put our little probe clip on here so that I can attach this into the circuit. And of course the receiver is off right now and it's disconnected from the line. So I'll put this on here like that, and I'll attach the ground lead to the chassis here. And the next thing we'll do is I'll turn the receiver back on and we'll take a look on the vacuum tube voltmeter. You want your vacuum tube voltmeter again on the negative DC volts, and you can have it on the 15 volt scale. The 5 volt scale is okay, but you're going to find you might come to the end of the scale and you'll have to bump it up one. So if you really have a badly mistuned IF section, you can start on the 5 volt scale or lower, and then gradually work your way up. I've got mine set on the 15 volt scale, and I'll show you that in just a moment when I reposition the camera. I've now got the vacuum tube voltmeter and the oscilloscope hooked up to this Echophone EC-1, and the power supply is back on again, so we're ready to do our tuning procedure. So I'll start exactly the way I did before. I'll go 1, 2, 3, and 4, and you can take note of the vacuum tube voltmeter. Again, we're tuning for a peak, and it needs to be on negative DC volts. This is an insulated screwdriver here. So you see how I passed it, so now you have to back up, and you want to get it to the absolute peak. Sometimes that takes a little bit of time. Sometimes you have to go back and forth until you find it, because you'll pass it a few times. So now we're going to go into number 2 here. And now we'll go into number 3. And now we'll go into number 4. And now we're peaked up. And that's how you peak up the IF section using a vacuum tube voltmeter and an oscilloscope. So on here again, you're just looking for maximum amplitude. And on here, of course, we're just looking for the highest negative voltage. So we're on the negative 15 volt scale right now. So we're at just below negative 10 volts on that AVC line. Before we start in with the RF alignment on this little Echophone EC-1, we're going to adjust the beat frequency oscillator. Now the BFO allows us to listen to Morse code, or if we're listening to an AM broadcast, we can align the radio here and get it right on frequency using the BFO. Another thing that we're going to want to put together here before we do the RF alignment is this little schematic right here. What this does is this basically tricks the antenna input system, or this antenna coil, into thinking that we have a 400 ohm input when we are using a 50 ohm output signal generator. If you tie your 50 ohm output signal generator directly to the input port on the back here, when you adjust these capacitors on the antenna coil, they will be misadjusted and you'll have a loss in sensitivity. So this needs to go in line with the signal generator in order to align this. Now many of these old receivers revolve around a 400 to 600 ohm input system. So what this does again is this just makes this coil think that we have it hooked up to that correct impedance. Now it's really simple to hook this up. All you do is you take the center conductor of your signal generator output, connect it to here, and of course the common lead of your signal generator connects to the antenna ground over here, like I've got it hooked up. And then of course the output here just connects to the antenna input of your radio. Now you don't have to be too specific with these values. If you have a 390 picofarad capacitor and a 390 ohm resistor, you're absolutely fine. So again, don't get too picky as long as the impedance is much higher than your signal generator. That's, as I say, again, this is more important for the RF alignment. You don't need this for the BFO right now. You can just tie it directly in. We're basically just cramming signal into here to align the BFO. Now you want your signal generator set at 455 kilohertz as before when we were adjusting the IF coils, and I have it set to about 200 microvolts. Now this signal level will vary depending on how your receiver is set up right now. You can up or down the input level, but I have mine at 200 volts because it's it'll work just fine at that. You also want to make sure that you have no modulation on your signal generator, so turn your tone off completely. If you have that tone on, it'll make this alignment very difficult. So there can be no modulation in your signal generator whatsoever for this portion of the alignment. You want a speaker hooked up to the speaker terminals again. Of course, this radio is always hooked up to an isolation transformer. Again, if you're not familiar with this, don't do this. And of course, anything that you're following along with, you're doing at your own risk here. So be careful because everything's open and you got alligator clips and everything in here. Okay? Now, tune the receiver, the little Echophone EC-1, to a quiet portion of the broadcast band, somewhere that's quiet, and turn the volume up. I usually turn mine to the bottom end of the dial or thereabouts. So here we have static right now. Now what we're going to do is turn the BFO on, and we should hear a tone. Now if this BFO is way out of adjustment, you won't even hear a tone, but you will hear a change in the pitch of the static. Alright, so I'll just turn the BFO on quickly here. You can hear we have a tone. So now we have two frequencies beating against each other, hence beat frequency. Okay, so basically we have our signal generator here, which is at 455, and we have the beat frequency oscillator here. So the difference between the two frequencies right now, where the beat frequency oscillator is sitting and where the 455 is here, is that tone we're hearing. So the further we move the BFO away, this from here to here in hertz is the tone that we're hearing coming out of the speaker. So what we're going to do is take the beat frequency oscillator and bring it as close to 455 as we can, and then we will basically have no difference and we won't hear any tone anymore. So basically it almost is kind of hiding behind this one. Okay, but once it starts to poke its head out a little bit on either side, we're going to hear a tone. So if we come up this way, we'll start to hear a tone, and then if we bring it down, we'll get 0, and now if we pass it, we'll start to hear a tone again. So we just want to basically have them aligned like that. Okay? And how we do that is we take a 1/4 inch nut driver here and we align this trimmer capacitor in the back of the receiver. So now this is a finicky adjustment, and of course it's kind of stiff and rigid, so sometimes you'll have to go back and forth a little bit and you'll have to really tinker with it because this is only held up by one little like a little metal pole that holds it up, and the whole system kind of moves around. It isn't really a they didn't mount it very well, let's put it that way. So what I'll do is I'll give you an idea here of how to adjust it. So what I'm going to do is put this in the back now, and I'll just get over here like this. See, I'm going the wrong way. See, now I came right to the 0. Now I'll pass it. I'll keep going in the same direction. See, it comes up on the other side. Now I'm at 0 again. Now I'm going to pass it, and I'm on the other side. Okay, right there. So now we have them really close to each other. So there's probably just a little bit off on either side, and it's very hard to keep this right at 0, but if you're not hearing a tone in the speaker and it's, you know, no flutter or anything, you can pretty much consider yourself having the beat frequency oscillator aligned. So what I'll do is I'll give you an example of how you can test that. So we'll go up to our signal generator here, and if I roll above the frequency, I'll adjust the hertz here, you'll hear that we'll start to get a tone back again. Okay? Okay, now I'll come back down to 455. Okay, now I'll go below 455 and we should hear a tone again. And that's how you tell that you've got your BFO aligned. It really is just that simple. We're now ready to start with the RF alignment on this Echophone EC-1, and the band we're going to start with is the broadcast band. When you do an RF alignment on a receiver, you usually always start with the lowest band, being the broadcast band, and you work your way up to the top band, which is usually ends up around 30 megahertz if you have a general coverage communications receiver. So I've got my signal generator set to 600 kilohertz. That's the signal that's coming out, and that's as per the instructions, and I will show you that here in just a moment. There's 100 microvolts coming out this cable right now, so that's about all the strength that you'll really need to do an RF alignment. If it's extremely far out, you might need 200 microvolts with this receiver, but 100 microvolts should be just fine for this band. I've got 50% modulation at 500 hertz on this 600 kilohertz frequency. So it's 50% modulated. I have a 500 hertz tone mixed in there with that. So when we're doing the alignment, it just aids us in being able to find the frequency on the receiver dial a little bit easier, because when you come to it, you'll hear that 500 hertz tone. The reason that I've chose 500 hertz here is just because the microphone picks it up. You can use whatever tone you want on the frequency, whatever's comfortable for your ear. So next, we'll take a look at the receiver and how we've hooked up the test instruments in order to do this alignment. In order to do the RF alignment on this Echophone EC-1, on top of using a signal generator, we're going to use a vacuum tube voltmeter and a speaker. And we're just going to tie all of this in, aside from the signal generator, to the two speaker terminals here. And this is really how it's done. So this one side here and this one side here are these two speaker terminals on the chassis here. So this side here goes directly to the speaker, and it also goes to the negative or common lead of the vacuum tube voltmeter. So they both tie to this one side. You can see I have two alligator clips here. On this side here, we have a 120 ohm resistor in line with the speaker, and we also have the vacuum tube voltmeter tied in right at this jack right down here. Now the reason that I have a 120 ohm resistor here is because when you put the speaker across these two terminals, it presents a really low impedance, and it's hard to get any deflection on the vacuum tube voltmeter. So by putting a 120 ohm resistor in line with the speaker allows us to turn the volume control on the Echophone EC up just a little bit, not enough to harm the output transformer, but it allows us to turn it up a little bit so that we can get meter deflection on the VTVM, and of course the 120 ohm resistor cuts down the sound so that the sound really isn't intrusive, because you got to remember you're going to have a 500 hertz tone coming out of here when we're on frequency. Now with this setup here, you have to use common sense. You're not going to be turning your receiver up full blast, because you only have a 120 ohm resistor in line with that transformer, and you don't have any impedance from a speaker on that one side. So if you change the impedance of the audio output transformer on this side, it gets reflected back into the plate circuit of the audio output tube. So you want to be kind of gentle on it, give it just enough volume so that you have comfortable VTVM deflection and just a little bit of tone coming out of the speaker. Alright, the vacuum tube voltmeter is set at 1.5 volts, okay, RX1 and the 4 volt scale here. So we're set on the 1.5 volt scale here, alright, and this is in AC volts. Make sure you have your probe on AC. That's an important thing to do. A lot of vacuum tube voltmeters have a switch on the probe. Make sure it's in AC. Alright, and at this point we're pretty much ready to get started with the alignment procedure. In order to start the alignment, first thing we want to do is look at their page and find out where they want us to align it on the band scale. So on the actual display dial on the front of the radio, we have to align the needle to these points while we're doing this. You can't just generically put the needle at any old place. You have to align it to the points that they want you to, or the needle won't track correctly. So it may align at, say if you're going to try and align this at 500 kcs instead of 600 like it says here, if you're going to try and align it at 500 and 1600, when you come to the middle of the dial, it won't track properly. You know, say 1000 or 1 megahertz would probably sit down around 980 or 970. So it's very important to align it to their exact points. And their points for the AM broadcast band are 600 kilocycles or 600 kilohertz, however you want to say that, and 1800 kcs or 1.8 megahertz are the two places they want us to align this. So they want us to hook a 200 microfarad, in today's speak that's 200 picofarad dummy antenna to this, but we're already using this dummy antenna here that we've made, and that's attached to the back side of the radio right here, as you can see. So the signal generator is coming into this capacitor, going through our dummy antenna into the antenna port, and of course the ground from our signal generator is just attached to the antenna common side, and again this is the common lead or ground lead, whatever you want to call it, from your signal generator coming out to there. Okay? So that's how we have that hooked up. Now it tells us that first up in here we're going to avoid a lot of what they're telling us here, because just like the way this radio was made, this is kind of a dangerous way to do things. They want us to put our vacuum tube voltmeter across the primary of the output transformer, and that would cause us to put our VTVM across the high voltage side of the audio output transformer. We don't want to do that, because that's going to make the case of our vacuum tube voltmeter live with about 100 and some odd volts DC, and we don't want to do that. So what we're doing instead is, like I just explained, we're just going to use the speaker output terminals here, because there's no high voltage on that side and it's isolated, and that's the much safer side to do it on, and that's the reason that we're using that speaker in line with a 120 ohm resistor and in that particular setup. And this way can be used for basically aligning any communications receiver. You can do it the same old way. You might need to change this value of resistor depending on the speaker you're using. If you have a really efficient speaker, you might need to, instead of using a 120 ohm resistor, you might need to use a 180 ohm resistor or something like that. This really isn't picky. As I said, all you got to do is just watch the volume control. Don't really crank the volume up, because that could be a little bit hard on the audio transformer. So now what it tells us is we want to adjust number 5, which is the pad, and we want to adjust number 6 and number 7, which are the trimmers. Now first here we see number 6, number 9, and number 11. Those three are the oscillators, and these three on the other side, 7, 10, and 12, are the antenna adjustment controls here, so we're going to be tuning this antenna coil. Now you can see I haven't fixed this one. This is for the broadcast band. I did some experimenting and I realized why they've taken this off, because any capacitance at all above what this is already at just takes the sensitivity away at the top of the band. So if I was to fix this and put this other arm back on here, I could basically leave it open without a screw. It would just be sprung up. So this really just wants no trimmer capacitor across this at all, and that's why I've left this. Putting one in here would simply be just for aesthetics at this point. As I say, I've put another trimmer across this one. It went from 2 pico to about 30 pico, and I rotated it, and it's all downhill from there. So this is absolutely fine. I don't know, maybe they even did that at the factory. I have no idea, because it's absolutely not needed, and there's nothing that really changes in this coil circuit. So why this is gone, either somebody else realized this earlier or this was done in the beginning. Now you'll see I've got some black tape here. I've got black tape here. This just denotes what I would be aligning. So if yours is here, you could try and align it. This just shows here. This black tape shows that I'm going to be aligning this one. And this black tape shows that I'm going to be aligning this pad control on this side. Now, this pad control has got a slot head screw on the other side. And if you don't have this special screwdriver that I've got with this kind of a square notch or rectangular notch in the bottom, you'll have to adjust yours from the top. So the radio would be on its side, and you'd have to come in from the top and adjust the this pad control from the top, and then do this from the bottom again. Now keep in mind that every time that you're in one of these things, this always has to be hooked up to an isolation transformer. You never ever work on one of these things without an isolation transformer. You gotta be very careful, and again, you're doing so at your own risk. There's a lot of high voltage under here, just take care. So now, it says here, number 5, they want us to adjust to at 600 kcs here. So this is number 5 right here, so we have to adjust the dial here on the face of the radio to be at 600 kilocycles. And I'll position the camera and be right back. So in order to align this to 600 kcs, we want to make sure that the band spread tuning is sitting at 0. So it has to be at 0 while you're doing all of this entire alignment procedure. If it's sitting up like this, you're going to malalign your radio. So it has to be right to the bottom, right at 0. And then what you're going to do is you're going to take this main tuning dial here and you're going to roll this to 600. So right on this bottom scale where it says number 1 and it's upside down here, we're going to roll that right to 600. Now 600 to my eyes is right there. Now the angle the camera's on, it might show a little bit different, but that's right above that line. So right now we're on 600 kcs exactly. Now you don't touch anything on the face of the radio with the band spread tuning or this through this entire procedure right now. Now that we have the signal generator set to 600 kilohertz and we have the dial on this receiver aligned to the 600 kilohertz mark, we're now going to bring the receiver onto frequency. So the signal from our signal generator is coming in the back of the radio through our dummy here right now. So what we're going to do is give it a little bit of volume, about a quarter of the way up. And this is the point that we align to align the bottom end of the band. So I'll turn this and turn it until you hear a tone. Okay, so now that we have a tone, we want to make sure that we're right on frequency. And how we do that is if you look at the vacuum tube voltmeter over there, you're going to rotate this back and forth until you get maximum deflection on the vacuum tube voltmeter. So I'll just remove the wide angle lens here. And I'll zoom into that a little bit. So now I'm going to rotate this back and forth, kind of like we did with the BFO, until we get maximum deflection. See, if we go a little bit too far off frequency, you see how the needle drops down? So we want maximum. See, I passed it there, so now I got to back the screwdriver up a little bit. And passed it again. There we go. So that's maximum deflection. So now we've aligned the bottom end of the band. I'll just turn the volume down here. We've aligned the bottom end of the band. So the next step we have to do is go to the signal generator and put the signal generator to 1.8 megahertz. That's the next step that they want us to do on this sheet. The next step is to tune the receiver to 1.8 megahertz, and there is no other pad to adjust, and we adjust number 6 and number 7. So here we are at the face of the radio again. So again, we don't touch the band spread, that always remains at 0. And we take the main tuning and bring this up to 1.8 megahertz. We can see 1.6, 1.7, 1.8. So 1.8 is this line that's right here. So again, I'm going to adjust this to where it's square on to my eye, and that's where it's square on. And keep in mind the camera's kind of looking in on a bit of an angle, so it might not look like I'm exactly on 1.8, but if you look at this straight on, it's covering up the little 1.8 mark. And that of course is on the number 1 little half moon here. Now that we have the Echophone's dial pointer set at 1.8 megahertz and we have the signal generator set at 1.8 megahertz, we're now going to align the oscillator so that way the dial is aligned. And this one here is the one that we align. So now I'm just going to turn this until we hear a tone again. Of course, I have my volume back up a little bit. So now we hear we have a tone. Now what we want to do again is peak that up. So again, we're going to look at the vacuum tube voltmeter. And we're looking for a peak with this oscillator now. So I'll stick my screwdriver in and I'll rotate it. You can see it's very touchy. So we're looking for a peak. And right there is the peak. So now the upper end of the band is aligned. So now what we do is we need to go check the lower end of the dial and see if it's aligned, because what it'll do is this will pull the bottom end out of alignment sometimes just a little bit. So we'll go back to the bottom end of the dial and we'll check that, and if not, we'll readjust that. And if we have to readjust that, we'll come back up to the top and readjust this again. I've got my signal generator set at 600 kilohertz again. And what we're going to do now is rotate this needle back down to 600 kilohertz on the dial here. Now, by adjusting that last capacitor to align the top end of the band, sometimes it drags off the bottom end. And what we're going to do is check the alignment down here. If it has moved the bottom down here, say the needle isn't exactly on 6 anymore, we'll need to go through this alignment procedure again and then double check after another procedure. So what happens in radios that have been really misaligned, you have to kind of work it in. Like you'll adjust this to 1.8 and it'll adjust to 1.8, and then the 1.6 will sit here. And then you go back and you adjust to 1.6, and then when you go back up to 1.8, it's dragged this end. So you're kind of in effect stretching the band out by adjusting those two capacitors, or you're shortening it up. So what we've done now is we've adjusted the top end again, so it may have pulled the bottom, or it might just be close enough to leave at 600, so we're going to check it out. And that's really how these align. So the pad is going to adjust the bottom, and sometimes the bottom pulls the top down, so then we adjust the top, and the top slightly pulls the bottom down, right? And it just kind of goes back and forth like that from the pad capacitor to the oscillator capacitor on that coil there. So again, we're going to move the dial to 600 kilohertz here. I'll turn the volume up a little bit. Okay, I'll look at that straight on. And when I look at it straight on, it's right on 600 kilohertz, so I don't have to go and do this band again, which is kind of nice. So this one is aligned up, so that aligns our broadcast band area all the way to 2 megahertz, which is basically the broadcast band through the 160 meter band, which is kind of nice, and that gets that one band done. Now band number 2 is exactly the same alignment procedure as band number 1, and of course band number 3 will be very close again. The alignment of band number 2 is much the same as number 1, it's now just different spots. So they say on band number 2 here that they want us to adjust the low end at 2.5 megacycles and the upper end at 7 megacycles. So we would turn the radio's dial to 2.5 megacycles, and we would also turn our signal generator to 2.5 megacycles, and then we would tune this side right here for 2.5. And once we hear the tone, just like we did on the previous band, then what we do is we tune our signal generator for 7 megacycles, and then we tune this radio so the dial says 7 megacycles. Alright, and then at that point we tune this capacitor right here on the oscillator coil so that we hear the tone again. And then at that point, once we hear a tone, we go over here and we peak that tone up with this capacitor. So we're just looking for maximum gain with this one trimmer cap here on the antenna coil. And that's all that these do, is these just peak the gain up, whereas these align the radio. They actually align the dial, this here, and of course the pad down there. Now on the uppermost band, which is the goes to about 30 megahertz, they want us to align it at 28 megacycles. Alright, and there is no pad control, so that we don't have one of these. So all we would adjust at that point is this center one, and then we would adjust this one here for maximum sensitivity. Now these receivers are a little bit quirky on the upper bands, and what I mean quirky is they have image frequencies and everything. This is only a single conversion super heterodyne receiver. So one of the things I found that really settled this down is I added this little 3 picofarad capacitor across the tuning condenser into the plate circuit of the oscillator. And if you look on John's schematic on his site, you'll see a little wire that looks like it has a hook on it. And this is just basically replacing that with a fixed mica value. That's all that's really doing. And that really helped settle down this this receiver on the upper bands. You got to keep in mind that nothing is shielded in here. There's no partitions in between any of the coils. And you know, making this receiver work up to 30 megahertz back in 1940 was really quite the feat. So it's you know, it's just the nature of the beast. This is a very simple little receiver, and there are a few image frequencies. So there are a few things that you can do to kind of help that out. As I say, this little 3 picofarad capacitor really helped settle down the oscillator in the 12K8 vacuum tube. For those of you that are new to the super heterodyne receiver, or for those of you that don't quite understand the principles behind the super heterodyne receiver, I'll give a quick explanation of how this little Echophone EC-1 works, and maybe that'll clear some of your questions up. So this is classified as a single conversion super heterodyne receiver, and when they say single conversion, that stands for it has one mixer tube. So if this had another mixer tube down the chain here and a different IF frequency and a different IF chain, it would be classified as a double conversion super heterodyne. And the same thing goes for triple and quadruple conversion. It just gets more complex. We have more mixer tubes and more IF chains at different frequencies. Now, super heterodyne stands for supersonic heterodyning receiver, and it really is an old term, and they've kind of narrowed it up to just super heterodyne. Heterodyne just means the mixing of signals. So a lot of confusion with the super heterodyne receiver revolves within this first little area here, and it really is due to the manufacturers of these receivers. They call this tube here in the front end so many different things. They call it the first detector, they call it a mixer, they call it a converter, they've got all sorts of different names for it. In all reality, this tube here is an oscillator in the bottom and a mixer on the top. There's two tubes in one here. It's kind of a complex tube, and we can see that in the numbering and lettering system here. This tube is called a 12K8. Now 12 stands for the heater voltage, and that's the amount of voltage it takes to light this tube up inside. It's actually 12.6 to be exact. K is the factory lettering system that just allows us to identify this tube, and 8 stands for the amount of useful elements inside this tube. And when I say elements, I'm talking about plates and grids and cathodes and filaments and everything. So if we look at this 35L6 GT over here, 35 stands for the filament voltage. That's the voltage it takes to make the cathode light up inside this tube. L, again, is a factory designation letter. The 6 is the amount of useful elements inside, and GT stands for glass tube. And all of this series of tubes kind of work within the same principle. Now, if you have a 7734 or an 8417 or something like that, you'll need to look that up in a manual because there really is no standard system for that particular numbering system. Now, these are all kind of standard tubes in an All-American 5, of course excluding this beat frequency oscillator. This tube here they've played with quite a bit, and I think they're using this 12K8 right here because it goes pretty high in frequency, and of course the filament current matches all the rest of the filament currents going through here. In order to run a series set radio like this where all the tube filaments are hooked in series, they all have to pull the same amount of current. Now, if, say, one pulls 400 milliamps and one pulls 200 milliamps, then, of course, the one that pulls 400 milliamps is not going to light up very well, whereas the one that pulls 200 is going to get very, very bright. So this is voltage and current dependent when you're putting all these tubes in series, at least the filaments anyways. So there is a lot of thought going into this, and these tubes are pretty well matched in order to make them operate with each other like that, because if one pulls a little bit too much, of course all the rest of the tubes are going to get a little bit brighter, and it's going to put more wear on these tubes. They're going to burn out. The filaments are anyways just a little bit faster. So getting back to this first stage here, of course, this being called so many different things, and of course them not labeling this section properly, what they should be calling this here in the oscillator section is a variable frequency oscillator, because that's exactly what this is. When you move that tuning capacitor, the main tuning capacitor, all it's doing is it's moving one of these coils around. It's shifting the frequency of this coil. Now this is the oscillator coils, and this is the antenna tuning coils. So if you notice inside the Echophone EC-1, on the main tuning capacitor, it has two completely separate capacitors that move in one case. They're connected by the shaft, but they're electrically isolated on one side. Now, one of those capacitors tunes this antenna coil here, and the other capacitor tunes the oscillator. And it's designed so that the oscillator is always 455 kilohertz above what you're listening to, and that's how you hear it. The difference in that is what makes the IF chain and allows us to hear what we're wanting to tune into. So again, if we are listening to, say, 1 megahertz AM or 1000 kilohertz, so we're listening to 1000 kilohertz. If we tune into 1000 kilohertz, this oscillator will be tuned actually at 1.455 megahertz or 1455 kilohertz in order to hear this. Now the difference between the 1 megahertz that we've tuned in here at the antenna to the oscillator in here being at 1.455 megahertz is 455 kilohertz between the frequency of the IF chain, and that will allow us to hear that signal through the IF chain, and that'll get into this diodes in this detector tube here, and it will demodulate that AM signal. This tube actually does three functions. It creates the AVC voltage, which is a negative voltage, which turns the grids off and lowers the gain of the tubes when we have a strong signal coming in. The diodes act as a detector and a demodulator. So what that does is that allows us to pull the audio off of the signal. And it also has an amplifier inside this tube, which acts as an audio preamplifier for this audio output tube, and this audio output tube drives this transformer, which in turn drives the speaker again. So the reason they have an audio transformer here is because the impedance of this tube is much higher than the impedance of this speaker, so this transformer really is just transforming impedances. And it's the same with this antenna tuning network in the front here. The reason that we have this tuning network between the antenna and the grid of this tube is because the impedance of this antenna is much lower than the impedance of this tube, and these coils in the front end allows us to better match the antenna to the tube. And of course, because we're tuning this section, that gives us a little bit of pre-selection in the front end and allows us to tune the antenna tighter to the tube. And of course, since it's tuned tighter, we get a little bit better, we could call it response coming in here. So it's going to have better adjacent frequency rejection is really what it's going to have. And that's called selectivity. So the more stages of RF amplification we have and the more tuned stages we have, the better selectivity we're going to have coming here. So of course, with more RF amplification, it's kind of a catch-22 here because we only have single conversion. If we had a double conversion, again, we would be able to have a little bit better selectivity in the IF department in this receiver, and of course we would have a little bit better adjacent frequency rejection again. So it really is a combination of matching everything together. But this receiver is a very simple receiver, and this is really quite functional. So of course, when we get up to around 30 megahertz or so, or up in the really high megahertz area, single conversion really isn't all that good anymore, and we should really have a double or triple conversion at that point. But for what this receiver is and for how it works, it's not doing too bad. So hopefully that helps you understand the way that this operates. Another quick, easy way of looking at this is, say we have all the frequencies here. This is the antenna here, and we have, this is the whole broadcast band here. Okay, so we have 550 kilohertz here, and we have 1600 kilohertz here, and all these signals are waiting to get in the antenna. Since we have these coils here, this coil here is being tuned, and this coil here is being tuned on the broadcast band, what we do is we have this being tuned. Say we're going to again listen to 1 megahertz AM. This will be tuned at 1 megahertz, and this will be tuned at 1.455 megahertz. So as we come up to 1 megahertz, as the oscillator passes over top of it, we're not going to hear it because where we're listening to is much lower than 1 megahertz at this point. So as we move this up, all right, now we're coming into 1 megahertz, and this is 455 kilohertz above. So now we can hear this frequency because this is tuned and this is of course above, and now we have the difference between the two is 455 kilohertz, which is the IF chain, and that allows the signal to pass here, and of course we can demodulate it. And that's a really simple way of looking at this. So really this is just moving up and down together. So as we move that capacitor, it's causing this section to track 455 kilohertz lower than this, and it's just doing this. Now some receivers are 455 kilohertz above and some are 455 kilohertz below. This oscillator is 455 kilohertz above what we're listening to all the time. That's how this works. This here is a beat frequency oscillator here, and that's what we ended up tuning before to listen to CW. Now that was that little variable capacitor on the rear of the radio that we tuned. Now how we tuned that again is we fed 455 kilohertz just into the antenna section and put a lot of force in there so it kind of crams it through the IF section here. And then what we did is we turned the BFO on and we zero beat this particular circuit so that there's no difference. This is tuned to 455 kilohertz, and this is IF chain, of course, is fixed at 455 kilohertz. So if we had any difference in the beat frequency oscillator, so say this was 455.500, okay? That 500 hertz difference we would hear out the speaker if we're tuned exactly to a frequency. So say we're tuned to exactly 1 megahertz AM, okay? And this is sitting at 455.500. We would hear a 500 hertz tone on that radio station coming out of the speaker. And that's really how this works to decode a Morse code. Now if you want to use this to decode single sideband, John at his website has done a really nice circuit modification for this in order to couple this to an IF stage that's a little bit before where they couple it in this circuit, and it helps to decode single sideband quite a bit nicer. So if you want to use your radio to listen to single sideband, I encourage you to head to John's website and check out his schematic and his little modification. He really did a good job. So that's really how this receiver works. Now keep in mind that these coils are on a double wafer switch in the front here, so that when we're on band 1, only this coil is connected to the oscillator and this coil is connected from the antenna to the input here. When we're on band 2, it disconnects this coil and connects this coil here to the input and to the antenna, and it connects this oscillator coil up to here and disconnects this first one. And that's how it works. It kind of goes like this, and like this, all the way down. So next what I'll do is I'll show you how this is actually functioning with a signal generator and an oscilloscope, and we'll be able to look at the difference in the frequency, and you'll see how that just comes into play. In order to explain how the IF section in a super heterodyne receiver operates, I'll use my signal generator here, the receiver, and an oscilloscope. So we can see here that the signal generator is tuned to 11 megahertz. I have 100 microvolts signal coming out of it. It's 50% modulated by a 500 hertz tone. So when we tune into this 11 megahertz signal, we should hear a 500 hertz tone. I have my oscilloscope hooked up to the oscillator portion of the 12K8, and we can read the frequency of the oscillator here and see how nice and clean the actual sine wave is coming out of that oscillator. And I have the signal generator hooked up to the back of the Echophone EC-1. Now the signal generator again is putting out an 11 megahertz signal, and there's a 500 hertz tone on that 11 megahertz signal modulated to 50%. So what I'll do is I'll rotate the main tuning dial on the Echophone EC-1 and we'll watch what happens. So if you watch the frequency counter, I'm going up in frequency here. Now you can see I'm around 11 megahertz here, but you don't hear a tone. And that's because the oscillator needs to be 455 kilohertz above what's coming in from the signal generator. So right now the oscillator's at 11 megahertz and the signal coming in is at 11 megahertz. So I'll keep rotating until we get to 11.45 and we should start to hear this. So we're at 11.31 now, 32. And you can hear we're at 11.45 right here. And then I'll pass it. And you can see I've passed it. So now I'll come right back down to 11.45. Right there, we're at 11.45. So you can see that's the difference between the input signal and the oscillator. The oscillator always needs to be 455 kilohertz above what we're listening to. To further understand the way a super heterodyne receiver works, I'm going to put my oscilloscope right here on this last IF transformer, right where it goes into the detector diodes. I'm also going to put my vacuum tube voltmeter over here on the AVC line. Then what I'm going to do is I'm going to hook my signal generator to the input here, and I'm going to feed a signal into the input, and we're going to tune into that signal with the receiver, and we'll look at the result at the end of the IF chain here. I've got the signal generator set to 2.5 megahertz, and that's running in on the rear of the radio just below here. And now what I'm going to do is I'm going to tune the receiver to 2.5 megahertz, and we'll watch what happens at the end of the IF chain. So now you can see I'm tuned into the 2.5 megahertz signal. Now that means that the oscillator in the radio is at 2.955 megahertz right now in order for me to tune this 2.5 megahertz signal, because the oscillator in this receiver is above the frequency we're listening to all the time. So now you might also be asking yourself, well, how come if the frequency is below 455, why can't it be above 455? Well, it can. So if I go 2.955 megahertz plus 455 kilohertz, let's see what happens. So right now, I'll just shut the signal on my signal generator off. Okay, and I'll type in 3.41 megahertz. And I'll turn it on. And you can see that we see that signal in there as well. But we don't hear that. And the reason that we don't hear that very well is because of that antenna tuning network in the beginning of the receiver that we originally talked about, which again is these coils right here. Alright, so what's happening is, again, there is a form of pre-selection happening in the front of the receiver on the other side. I'll just turn the volume down here. On the other side of that capacitor, so one part of that main tuning capacitor is tuning the oscillator, and the other half of that main tuning capacitor is tuning that antenna coil. But the antenna coil is tuned to be further down the band. It's tuned to be in the 2.5 megahertz range, not tuned to be at 3.41. So by doing that, we get a form of pre-selection. And what that's doing is that's really narrowing down the front end of this receiver so we don't see this particular, you could call this almost an image. So we're not going to see that. So what I'll do is I'll go back to 2.5 megahertz, 2.5 megahertz, and we can see how nice and strong that is. And the reason that this is much stronger is because it's below the oscillator. It's negative 455 kcs down. Now you can see on the vacuum tube voltmeter here that we have just about negative 3 volts. Now when I tune the receiver off frequency, you'll see that the amplitude dies down at the end of the 455 kcIF chain. Alright, and then when I tune it back into 2.5 megahertz again, when I tune it for its absolute maximum, we can see that we're right on 455 kilohertz. And we see that, again, we have just under negative 3 volts. Well, this is the AVC voltage, or the automatic voltage control voltage that's created by that detector diode at the end of the IF chain. Now, what that's doing is that's taking this signal and turning it into direct current, but negative direct current, and it's feeding it back to the grids of the two tubes that are ahead of this, which is the grid of the mixer tube and the grid of the first IF tube. And what it's doing is it's applying negative bias to those tubes to effectively shut the tubes down. So it's reducing their gain. So in effect, the automatic voltage control is really the same thing as you having your hand on an RF gain control and riding that RF gain control when you get a very strong signal, except this is doing it all automatically, so you don't have to turn the gain down when you have a really, really strong signal. So if we didn't have this section inside the radio, what would happen is the really strong signals that we're receiving would overload this receiver, and it would sound all distorted in the audio when we're listening to it. So the stronger the signal, the more negative voltage we're going to get. So if I up the signal coming into the receiver, I'll just turn the strength of this signal up. And you can see the signal's gone up, and so has the negative voltage. So by this coming up, this is compensating and of course bringing the gain of the receiver down just a little bit more so that it doesn't overload. And we can see on here that we're now exceeding the graticule on this oscilloscope. And that's really how the IF section works inside a normal super heterodyne receiver. So again, we have our frequency at 2.5 megahertz. That's coming in. That's in the back of the radio at the antenna jack. The oscillator is actually oscillating at 2.955 megahertz. The difference between the two is 455 kcs, hence this is a mixer right now. And then at the end of the IF chain, this is what we see. Now the audio that you hear coming out of the speaker is contained within this signal, and that's what the detector does. It detects the audio at the end of the IF chain, and of course it goes from there into an audio amplifier and out the speaker. Now that this little Echophone EC-1 is restored, let's check out its performance on the bands. We'll start with band number 1 here, which is the first little half moon. That first little half moon starts at about 550 kilohertz and goes to just above 2 megahertz. So it's the AM broadcast band through the 160 meter band just above 2 megahertz. It is the night time here, so we should be able to hear radio stations from all over North America on the AM broadcast band. So this really is a good time to test the performance of this little receiver. So let's give it some volume and start listening.
E-waste end up?
So for most nations this year,
gambling, Nevada didn't have a homegrown industry. So every time a new hotel...
which solves casino marketing.
The bread or the organization?
The organization.
And certain emojis.
Donate. Go to cardsforkids.com.
Attorney for your divorce is one of the most important.
Represents the movement.
Right.
You cannot make...
Personnel, their training. You have an item about this in your chapter.
Other groundbreaking ideas from that time.
Stories we're following for you right here on First Look.
And by both.
We have seen
Holes and 80. Tampa, a chance of scattered thunder.
That's why I recommend A Place for Mom, the nation's largest senior living referral service.
Referral service. About it to an independent referral insurance agency. Do you know the #1 cause of...
So that's pretty much the end of the AM broadcast band there, and now we're in the 160 meter amateur band. And right at the end of that, there's a bunch of computer-generated noise here. So, and that's about all there is right there at this time. So I would say that it's performing extremely well for this little Echophone EC-1. It really is it's quite the little receiver for its size and for really what it is. So let's try band position number 2, which is from about just below 2.2 megacycles to just above 8 megahertz here. And since we're at this end of the band, we'll just cruise backwards here. Bunch of computer-generated noise there.
What's going on is a large-scale military...
You should be able to hear broadcasts from all over the world in these bands. Lots and lots of shortwave broadcast here. So we're coming up on 5 megahertz right now, and the WWV should be there, and that's the time signal. There it is. It's nice and strong. Now, if you want to use the band spread scale, you have to move the needle to pre-aligned little markers on the band here, and then it'll give you a spread of the band. So really what it does is it just spreads the band out. How I usually use my band spread is I bring this here to about 10. Alright, and then what I do is if I want to fine-tune a station, I'll get onto a station here. I'll find a small station. We'll go back up this way.
Miners who are reaching out to the oath keepers.
Okay, right here's a nice touchy little station. Now you can see so it just helps you fine-tune the band. That's all it's doing right now. So you can see as we're going up with this needle, we're going down the band. And all that does is really give you a fine-tuning. But you have to realize that when you use the band spread scale, if you're on just any portion of the band, it will decalibrate the band, it'll spread the band out. So usually what I do, as I say, I just go to about 10 and then I go to either side of the frequency if I need to fine-tune something. So let's keep cruising this band here. Now we're in the 80 meter amateur band right now, and usually below that there's not a whole lot of action at night. We should have another time signal down at 2.5 megahertz, so I'll just roll down here and we'll hear that.
9 hours, 22 minutes.
And that's at 2.5 megahertz there. And that's the other time signal. So the time signals are at 2.5, 5, 10, 15 megacycles, and I think sometimes 20 also depending on conditions in the day. I'm not sure if they've cut some of the frequencies off or if they still have them all active, but I know that 2.5, 5, 10, and 15 are still active. I think 20 is still active too. And that's pretty much the end of this band. So now we'll head to band number 3, which starts at 8 megahertz and goes right up to 30. Lots of computer-generated noise. Sounds like galloping horses.
Is played. The Defence Minister, Jerry Bromley, attended an NZ.
That's the 10 megahertz time signal up here.
Are coming out of Greece, so
the audio control on this radio is really sensitive. It has lots and lots of audio gain. I'm pretty sure you could probably destroy this little speaker on the top of the receiver with this audio gain here. And it usually starts to get pretty quiet around 20 megahertz, I find. Yeah. Nothing really up in here right now. The conditions are out for this portion of the band. So it'll be pretty quiet above 20 megahertz. So it's actually working very, very well. I'm very, very surprised at the performance of this little Echophone receiver. For, you know, a little, basically, well, it's a 5-tube super heterodyne receiver with a BFO option. Now, I didn't hear any Morse code to try this on. If I heard Morse code, I would have clicked the beat frequency oscillator on so we could have listened to it. But, again, I'm very, very surprised at how well this little simple 5-tube receiver with a BFO tube on top, so really I guess a 6-tube receiver, is working. Quite impressive. Well, we've come to the end of another restoration project. I hope you enjoyed following along as I restored this little Echophone EC-1. If you did, give it a big thumbs up and hang around. I'm sure there'll be many more just like it in the very near future, with a lot of little projects sprinkled in between. So take care. Bye for now.